Well, good afternoon, everybody, and welcome to this meeting on data rescue. It's good to see you here in person, and also welcome to, I think, roughly 50 of you watching and listening virtually. So good afternoon. I hope we have a useful and informative meeting. My name is Julian Mays. I'm Secretary of the RMETS History Group, and this is a History Group meeting or organised meeting, but obviously the October national meeting of the Society. So this also is a bit of a milestone for the History Group, and there are some of you I know are History Group members. It is our 40th anniversary. So as we thought of the meeting, or rather I did, this is the obligatory plug, which I think we're allowed. Membership is free. That would put you onto our mailing list, and you'd be the first to see our newsletter. And there's more information about the group, of course, on the Royal Met Society website. Okay, and we seem to be looping slightly early. If anybody is persuaded to join our group, you would be very welcome, as long as you're an RMETS member. All you need to do is catch me sometime this afternoon, or if you're joining remotely, just to drop an email to the email address that you can see at the bottom of the screen there. And let's go back 40 years briefly. In 1983, the purpose of the History Group, I think, was to bring a generation of meteorologists together to collect their memories, to commemorate past weather events in previous decades and centuries. I do keep noticing it when it jumps forward like that, but it's not me. But the key aim of the History Group, of course, was to look at the changes in the science of meteorology and physical oceanography. And one thing the group did at that time was capture the memories of meteorologists who worked in the Second World War. And they were still around at that time, and two conferences were held in the 1980s. Now that brings us on to the purpose of the History Group today. And there was always an awareness in the past that it is not a climate change group. And one chairman in particular held that view. I would say now we cannot ignore climate change, however. If we remember, 1983 was several years before temperatures in the UK started to rise, despite July of that year being the warmest month on record at that time. As a mystery question, and I expect some experts here to know the answer, I wonder how many times since then the UK extreme maximum temperature has been broken, that record. I suspect I'm waiting for someone to shout it out. I think it might be, I can see some calculations here. 4. I thought it was probably 4. Okay. But because of that, I think we recognise, as people interested in the history of the subject, the great value in extending instrumental records as far back as we possibly can to put modern records into full perspective. And it seems to me that that is the logical intersection between the History Group and the field of climate change in general, even though we're not a climate change group per se. And that, of course, brings us on to data rescue, today's subject. So there is a timeliness or maybe an urgency to get more information from all archive records. Now, before we hand over to the first speaker, Catherine Ross, I was told it wasn't going to do that. Just a health and safety announcement. First aid, if needed, is available from Hayley and from Catherine, the Royal Met Society hosts today. No fire drill is expected, but there are 3 fire exits in this lecture theatre, 2 at the back and 1 just to the side there. And I think now just a quick word about Zoom for those of you joining us that way. Do please answer or ask your questions in the Q&A section. as you think of them. The Society Chief Executive, Liz Bentley, very kindly is sitting at the back with the laptop, able to field your questions. So at the end of each talk, we will have questions from both the hall and also from those joining virtually. The system does work very well. And if, to save repetition of the same question, if you see a question that you support, you can, I believe, upvote the question on Zoom. But thank you to Liz for taking on that essential role. So I think we just ought to mention very quickly Met Matters. This is a very interesting part of the Society's website, certainly existing as a web page. I'm not sure you can actually sign up. I did visit the web page yesterday, but Liz is nodding. You can still sign up to get further information there, and it's full of a lot of very topical weather and climate blogs if you're not aware of that already. Okay, so let's prepare to move on to the first speaker. And I'm sure you've all noticed at the bottom of most Met Office web pages, there's a link to the National Meteorological Library and Archive. Now, the first speaker, Catherine Ross, I'm delighted to say, is now the manager of that facility, and that's a very recent development. Catherine has also been a committee member of the History Group for quite a while, and she's going to talk about the data rescue strategy at the archive at the Met Office, highlighting the importance of metadata and access to data at that particular gold mine that some of us know well. So I shall hand over now to Catherine and her presentation, which hopefully will appear.
Slightly onto the page.
There we are.
Let's see if we can. Just going to go back to the actual start of my presentation. There we go. This could be entertaining for the day. I will try and keep track of the fact it obviously keeps moving for all of us, not just for Julian. Yes, so as Julian mentioned, I'm an archivist, but I'm now the Library and Archive Manager at the Met Office National Meteorological Library and Archive. We're down in Exeter, so that was a fun trip up today. Several of us, I think, can account for. Yay, it moved. So what sort of things do we hold in the archive? We hold the national memory of the weather, which in short consists of UK data, metadata, and a large collection of international data. We fulfill the statutory requirement of the Met Office under the Public Records Act. So basically, we have everything that was produced by the Met Office from its foundation in 1854 until going digital. Of course, we still collect a large range of records, but they're now largely in digital format rather than paper format. So there's not that much still coming into the actual archive, but there's plenty going into our digital archive. In addition, we've got private weather diaries and ship logs, which help us to extend the collections back before 1854 and to fill out the network whilst the number of official stations was still expanding. And whilst much of the material was produced by the Met Office, we also hold the Royal Meteorological Society archive on site in Exeter as well. So that's a really valuable resource, and particularly of early data, private weather diaries, and a wonderful collection of rare books. So if you're ever wondering where your archive is, we look after it down in Exeter. And in addition to the UK data, we hold a vast amount of international data. Largely that's published, but it's not always easily available elsewhere. And that helps us to place the UK data into context. So some of the key UK data collections in the archive will be ship and lighthouse and light vessel logs, climate returns, rainfall series, the vast rainfall series, daily weather reports and daily aerological reports, upper air that is, daily registers, which give us sub-daily data, autographic data for every weather element, and charts, many charts. Basically, that gives us enough shelves to get you up Ben Nevis 3 times. Probably including the Ben Nevis data now, actually. In recent years, there's been significant interest in data rescue activities, many of which you'll hear about today, many of which use stuff from that archive, and they involve various of the collections. But recovering the data has only limited value unless you also recover the metadata that goes with it. So I'm going to focus a bit today on the metadata side of things, because you're going to hear lots of talks about the data side of things from other people. I'm winning. Metadata can be found in many places. Station inspection documents, like the ones you can see here, are probably the most obvious source of information. That's where you'd go first. And they give a wealth of data about observing stations. So the examples here you've got are all inspectors' notebooks from the 19th and 20th centuries. So they include things like site plans up in the top. They're really helpful if we want to understand site moves, proximity of buildings, trees, exposure, all that sort of thing. Information about which observations are made, exactly how, even which set of instructions was in use at the time. So top right, it notes that the inspector's manual of, I think it's 1964, was in use. Well, of course, if that's 1980s, things will have moved on, and that might help you to understand why your data doesn't quite make sense. Site names, variations thereon, which can lead to a lot of confusion unless you can line all these things up and realize it's the same site with about 4 different names. Heights of instruments, regularity of inspections, and comments on the quality of the site, which can help to understand whether the data is likely to be reliable. And also some station histories include photographs, which are fantastic for understanding exactly where the site is and what's going on with it. We wish there were more. Metadata can also be found on the data itself, as in the climate return you can see on the bottom right, which gives us things like location and height information. Then they're on the covers and inside pages of the data volumes. So this middle slide gives us a ship's log, which has got lots and lots of data about the particular instruments in use and their calibration. And then in manuals, keys, decodes, and publications. So top left, we've got a manual on maintaining instruments. Really handy if you want to understand how an instrument was made and maintained, and therefore what might have changed in the course of its use. The top right, decode for report number 10, which happens to be the Royal Chartered Gale chart, so I'm a little bit keen on that one. And on the bottom left, we've got a couple of publications. So they're the hourly observations and the stations of the second order, just a couple of data publications, but they show you the various metadata that also gets included in those publications. And they also tend to include some of the errata, which don't necessarily turn up elsewhere. So they're quite a useful source that you don't necessarily expect to go to. And sometimes metadata can be found where you least expect. So seen in isolation, this thermograph trace from the HMS Prince of Wales might look somewhat suspect and make you question the accuracy and the calibration of the instrument. And therefore you might start thinking about, can I use any of this data? That is until you look at the corresponding barogram on the left, and discover that the origin of the anomaly is neither calibration, atmospheric, or geological. It was caused by the shaking of the vessel whilst firing upon the German battleship Bismarck. So with that piece of metadata understood, we know that all of the other data from both the instruments can be considered reliable and can be used. As I say, metadata where you least expect it. Why does metadata matter? Metadata is crucial to explaining, understanding, and having confidence in the data. Some of the questions that it might help with are just listed above. So things like, where is the instrument or the site? Did it stay there? Did it move? How often and by how much? What instruments were in use? How they worked, when they changed? A step change in the data might well be because an instrument was changed. A gap might be because the station history notes a broken instrument or a broken measure. Or we're still waiting for our measure. Please, can somebody send it again? You get a lot of notes like that. How and when observations were made. So practices have changed over time, everything from time of day to what units were in use. And in a long data series, you really need to consider if all the data you're looking at was collected at the same time and in the same way, because it almost certainly wasn't. And of course, it can help us to work out the reliability of the observer. So particularly inspection reports will indicate whether the observer tended to be usually accurate in their observations and on time, or whether they tended to over or under read an instrument. Needs new glasses, should have gone to Specsavers. Other opticians are available. And therefore, obviously, you can smooth accordingly. So it is useful data. So a couple of examples of how we as the Library and Archive collaborate on metadata in practice. So obviously, probably the key one for us is cataloguing. We're starting to catalogue the climate and rainfall station history files to help everyone to identify exactly what we have and understand what sorts of information are included in there. So we now have in Exeter all of the available files for England, Northern Ireland, Scotland and Wales. That's a lot of folders. There are a great many, and it's going to take us time, so please bear with us on this one, but it's a priority and we understand how useful it is to the data rescue community. We're also carrying on long-running digitisation programmes, which include a number of metadata sources. They include not just the station histories, but also sources of metadata such as observers' handbooks, manuals, annual reports, and of course, loads and loads of data. We've already seen a few examples of that. And then we share as much of that as we can on our digital library and archive, which, as a quick plug, is a free platform, which you can view and download everything on, which we digitized so far. Just Google it, check our web pages, you'll find it. Sadly, GDPR means that unfortunately we cannot share the station histories, which would probably be the most useful thing of all, but they've got lots of personal data in them, so we are not able to share them. But we can provide redacted information if you put in an inquiry, so we can still make it available. It's just not quite as easy as click and read. And we support a wide range of data rescue activities by scanning data and publications, which projects can then use to pull together complete data and metadata series, of which more at least from Ed later. And then some real-time applications to try and put that into context. Centennial stations are WMO recognised sites, which have a long and reliable data series and good supporting metadata. There are 410 centennial stations globally, of which 11 are located in the UK. So Balmoral and Rothamsted were recognised in 2017, Morpeth Cockle Park and Lisdinham in 2018, and Durham and Sheffield in 2023, so only this year. In all those cases, the nominations drew heavily on the station history files from the archives, which the observations teams and NCIC used to produce thorough dossiers of station history, which was then used to support those applications. Then there's quality control. So reviewing data series against nearby data sites helps us to identify inhomogeneities. Metadata can then be used to establish the reason for those. So in a recent live example from Lucas, minimum temperature suddenly showed a 3-degree step change in 1957. You can see that at the yellow highlighted section on the graph at the bottom. This was not reflected in any nearby sites, and there wasn't a mini ice age there. So it raised two questions: why the change and why only in minimum temperature? Checking the metadata revealed that the site changed to a much more rural location in 1957. Aha, this could certainly have caused a change in minimum temperatures, but it should also have been reflected in the maximum temperatures, so further investigation was necessary. So after reviewing how and where the observations were made, the QC team then moved on to when. And they discovered that before 1957, observations at the site were only made between 7 AM and 6 PM from 1921 to 1946, and then became between 9 AM and 9 PM from 1946 to 1957. So in other words, the daily minimum was taken over 11 or 12 hours during the daytime, and there was no overnight observation, when the lowest temperature would be expected to occur. After 1957, the site started reporting over 24 hours. This, of course, explains the breakpoint in the data. Now it's reporting overnight temperatures, and now, of course, we can understand why it suddenly drops by 3 degrees. But it has always been reporting during the day, so there's no significant change to the daytime temperatures. So this is a great example of how analysis of metadata can help us solve an inconsistency. But it also shows it's really important to keep questioning until everything makes sense, because the first solution is not necessarily the final one. And then it wouldn't be right of me not to talk about the relevance of metadata to climate change research, because it's crucial. The Met Office National Climate Information Centre, representative here today, recently published a paper which used metadata to examine homogeneity of temperature and humidity data for long-running stations. The study looked for breakpoints, a bit like the one I showed you earlier. In this case, you can see slightly different on the graphs. A breakpoint can be caused by changes affecting the instrumentation, Radiation screens, like the change to plastic Stevenson screens in 2002, which you can always spot in the data, local environment, measurement procedures, and stationary locations, all of which are types of metadata. The study found that temperature measurements in the UK over the last century had in fact been taken with a high degree of standardization. But when homogenization is applied across the complete data set, it results in a small increase to the existing warming trend in most variables. So to quote from the article, the average magnitude of trends in the uncorrected temperature data was underestimated by 5 to 10% when considering the last 100 years. The effect is negligible when considering the last 50 years. So to explain the graphic a little, when the values are below 0, in the negative, this indicates the original unadjusted temperatures were potentially too warm in that period. So with the dashed and dotted lines that you can see above and below the main bright coloured line, showing the adjustments applied to the warmest and coldest days. So we can see here that for TX, which represents the maximum daily temperature, the mean TX adjustment before 1900 was negative, indicating temperature observations themselves were too high. The largest adjustments were applied to the hottest days and the lowest to the coldest days. So there's something going on with warm temperatures here. And we can also see there's very little adjustment being made to the daily minimum temperatures, which are represented on the TN graph. TA and TW, by the way, are wet and dry bulb temperatures. So there's a trend here. What might it be? Well, one option is it might relate to the exposure and sighting of instruments in the earliest period of the data sets, resulting in a slight warm bias in the late 19th and early 20th centuries, relative to modern standards. So an example might be a Stevenson screen placed closer to a hedge than we would now normally do, resulting in a warmer temperature observation than would have been the case if the screen was sighted and exposed as it would be today. And the largest adjustments applied to the hottest days, with very little to the coldest days, is also consistent with what we might expect from less effective radiation screening in the earliest period. So before Stevenson screens come along, basically, or at least before they're necessarily consistent throughout. This is a hypothesis. It fits, it's a good one, but it's a hypothesis. So gathering more station history data to confirm whether the breakpoints and the trends do actually match with the adoption of Stevenson screens at each site will help us to confirm whether the explanation inferred from the statistical analysis actually matches with station histories. So this is a clear example of the fact that metadata is the only way we're going to solve what's going on with that statistical analysis. Another important outcome of the metadata study was to show that variations in how and where temperature observations have been made over the last century are not the cause of the UK warming trend. Indeed, if anything, the evidence is pointing in the opposite direction. So, in conclusion, you will hear reference to materials from the National Meteorological Archive throughout this afternoon. We hold the source material for a vast range of data and metadata rescue activities, both current and potential, and we expect to be supporting data and metadata recovery activities for many years to come. In fact, we certainly hope to be doing so. The archive really can be compared, if you like, to a data recovery goldmine, hence the title of my talk. Some of the seams are being worked, some have more potential waiting to be unlocked, and some are yet to be widely explored or even discovered at all. I think we probably have time for some questions.
Yep, can you hear me? So this is a question from Phil Jones online. Well, two questions. One is, the first question is, are the data series available for all the UK Centennial stations? So are they all available?
So one way or another, yes, they will be. So they're either available through CEDA or they will be scanned and through our digital library and archive. It depends on how you want to see it, really. What you won't see through CEDA is the last 2 years of data because it's yet to be QC'd. So that you have to come directly to the library and archive to access.
And the second point is more a statement, really, but as an aside, it doesn't seem that the availability of the long data series is a factor. For many countries, all we can find is the site names or lengths of record. It seems the WMO should have insisted that the data for the long series was made available.
Yeah, I agree. I think it's more a statement than a question. We're doing what we can down in Exeter. We are the UK National Meteorological Archive, so we have to use our funding to focus on UK data. But we do support other international exploits, so particularly Rob Allen and the ACRE initiative. We use that money to fund all the data recovery from all sorts of parts of our collections. There's one down here.
Thank you. I would like to say, first of all, that the people in the archive are extremely helpful when they're contacted. They go out of their way to provide what you ask for. It's really very helpful. But a question, you made the statement there that all the data from all the UK countries are available in Exeter. And I was of the understanding a lot of the Edinburgh archive had been sent to the National Archive in Scotland, which is a real pain. And I would try and encourage you to centralise it all in Exeter so that we know where to go for the data, and I'm sure get a better service than we can get from the National Archive in Edinburgh, because you can only take so many items. And because I come from the Orkney Islands, to go to Edinburgh for 2 weeks to take out all the data is well nigh impossible. So I can only plead with you if you could transfer it from Edinburgh to Exeter.
Yeah, so what I was commenting on was the station histories are all in Exeter. The data for Scotland, yes, it is largely held at National Records of Scotland, which does have different access arrangements. Some of it has been digitized, but only a very small amount. I think the main reason for that is, other than the fact that I'd need a new archive to fit it in, what we've tried to do as a UK government organisation, an arm's reach body, working with other countries, you know, Scotland, Northern Ireland, we keep the data in its country of origin because it essentially belongs to that country. So we've kept the data in Scotland because it belongs to Scotland, but it does make it challenging to get to. I completely agree with that.
But if you're British, you should be
I don't think I can really comment on that. I think there was another question over here somewhere. Oh. I'm sending Catherine running around the room.
Thank you, Catherine. So Alan Heisman from the History Group. My first job in the 1960s in the Met Office was extracting data from old ship's logbooks, as well as at that time the fleet of 700 voluntary ships that were still sending in data. And it came home to me then, on the old ship's logbooks, they were, say, throwing the leather bucket over the side of the ship, pulling it up, sticking a thermometer in it, and telling us what the sea surface temperature was. In those later ships, they were measuring the intake temperature from huge tankers as they sailed through the water. So they were drawing in different types of temperature. And it always worried me that sort of pattern over many, many years has continued. So trying to standardize those. And nowadays we've got satellite data taking sea surface temperatures. I find it very difficult to understand how you could ever homogenize all these records into a direct comparison. These days, you're measuring to fractions of a degree centigrade, whereas in the past, you had whole numbers of Fahrenheit. You know, have you any comment? It's not a statement, I understand. It's not a question to you, but have you any comment on how you'd ever try and cope with that sort of standardization?
Thankfully, I'm not a climate scientist, so I don't actually have to solve that problem. She says, looking at two climate scientists who do. But yeah, it is a real challenge. Mark may be able to comment on that. If you want to bring the...
I mean, you're absolutely right. The scale of the challenge is huge, but there have been people looking at it for several decades. So trying to understand the corrections for actually, Chris would be a good person to answer this question. To understand and make the appropriate corrections for the buckets and the different type of SST measurement that comes from engine intakes or from more recently from buoys and satellites is a big undertaking. And there is a body of literature that has been exploring exactly that topic for many years to try to pin down those uncertainties. So yeah, I don't know if Chris, you want to add?
Yeah, thank you very much, Mark. There's this work done that way. There are other methods of doing it. Was published in the Quarterly Journal in 1995. So if you've got access, and then the data was updated by Rayner et al. In the JGR in the very long paper on on HADIST and HADMAT. But the 1995 paper essentially tells you how we did it. The Americans have a different method. They use night marine air temperatures, which they can correct as well to some extent, but they're much more homogeneous than the sea surface temperatures. We actually looked at that as well in our early work, but that's not the way we actually do it now, but the Americans do that way. And the two methods actually agree fairly well. And this is all reflected in the way that the Intergovernmental Panel on Climate Change reviews climate change and sea surface temperature. So please read the 1995 paper for a start. Thank you.
So we've got two over here, and one in the middle. I'm aware that time is also getting on, so Julian, do you control it?
Hi, I'm Fiona Williamson. I've worked extensively on the ACRE project with Rob Allen. One quick question. I know that your main focus is obviously on the UK records, but are there any plans in the near future for UK colonial records to be digitized and put online?
So essentially we have to work with an available budget. So yes, I think within the near future, it all depends on budget. So I wouldn't like to put a timeline on anything. But certainly some have already been made available through some of the ACRE scanning, as you know. But yes, once we've finished the big series that we're currently working on, then certainly I would look at some of the colonial records to see what's our best approach to that. We need to think about a number of different aspects, including sort of what's the fairest way to approach that data. But it's certainly something that I would want to look at.
A question from online. So this is from Mary Curley. A statement, first of all, so thank you again to Catherine and the rest of the archive team, always extremely helpful in any requests. Kind of follows on from the last question, but do you have any information from Ireland? So anything like station inspector records, for example, from Ireland?
So Mary and I know each other well. So yeah, I think we've shared most of what we've got for Ireland. We do have a few station inspection reports now that go down into that area. They only came into the down to us, or we moved them across from a location in Northern Ireland to us in April. So we're still sort of in the relatively early stages of working our way through that. But yes, we've got a handful. It's not a large number that will take you back sort of pre-partition. There's one in the middle. But yeah, Mary, just email and we'll talk to each other.
Thank you. A really nice talk. I'm just thinking about reanalysis. And obviously that can sort of highlight biases and observations and estimate observation errors. Obviously that comes with, caveats as well. But is there any sort of way in which you sort of, you could use that to inform where to look for metadata to try to resolve discrepancies between reanalysis and the observations?
Short answer is I have no idea. I think reality is that we're collecting metadata from every source that we know of. So I'm not sure that it would necessarily point us to another source. It might help to focus on which particular source would be more helpful with a particular question. But I don't think it would identify any more sources than we already know of.
Well, there's one sort of particular case I had in mind was from Gibraltar that I looked at once. And there was a report saying that the sailors were recording the minimum maximum temperatures from the wrong end of the pin. So, you know, those kind of things, you know, might not be, well, you know, it may be in some metadata, but it would maybe point to try to resolve those kind of issues.
Yeah, I think it's just a case of, you know, that's where we just need to collect as much as we can, you know, and if we can bring sort of one source of metadata, that's never going to be the case. But if we can make all of the available sources of metadata as clear as possible, then it will, and some of the cataloging will help with that. Then it may help to pick out things like you've identified there.
Okay. Thank you very much indeed. Thank you very much indeed, Catherine. And just to reiterate the point that Keith made, I think we do need to recognise the debt of gratitude for so much of material being available online from the archive. It was unimaginable, wasn't it, a decade or so ago? Something we often refer to in the history group. Okay, before I hand over to Stephen Burt, I should add that with time being a little tight this afternoon, if you see me when you're speaking, if you see me stand up, it means your time is up, I'm afraid. But also thank you, Catherine, for allowing the panel discussion to start. I'm conscious that I haven't scheduled a panel discussion at the end, but if we do have time for discussion, as we've just had, I think that would make the afternoon more useful. And thank goodness you did find a train eventually, because I think that's a good starting point for this afternoon. However, let's move on to Dr. Stephen Burt, well known to many of us for his work researching different aspects of the climate of the British Isles, and for thousands of photographs, or maybe hundreds, published in Weather over the years. In particular, reference to today's topic would be the book on Oxford weather and climate since 1767 that Stephen recently co-authored with Professor Tim Burt. And anyone who has read that book would value the importance of the Oxford Radcliffe Observatory record. So Stephen this afternoon is going to talk about work to lengthen that still further, partly via citizen science work. I did repost this morning a tweet from Ed Hawkins suggesting that current research on Oxford air pressure is ongoing. I don't know if that comes into your topic at all, Stephen, but I'll hand over to you now so we can stay on time. Thank you very much.
Well, good afternoon, everybody, and thank you very much for the invitation to talk this afternoon. So I'm going to talk more about broadening the Oxford record rather than lengthening it, for reasons that will become apparent as we go through. So a quick sort of recap of the Radcliffe Observatory record. The observatory was built as an astronomical observatory, started building in 1772, finished in 1797, almost as long as HS2, I think. It cost at the time £31,661, 6 shillings and 11 pence, which in today's money is about £4 million. So a fairly large budget. Now the meteorological records there began really as soon as the site was prepared in 1772. They're a bit sort of broken up to about 1810, but then they're pretty well complete, at least in terms of temperature and pressure, since 1813, and sub-daily records all the way to 1924. And it's the longest unbroken single site temperature and pressure record in the British Isles, and it was awarded a WMO Centennial site in 2017. Now, the astronomy moved away from there a long time ago, in 1935, and since then the site and the meteorological records have been maintained by the Department of Geography at the University of Oxford, which I'm grateful to them for access to the site and to the records. So here's a summary of the records. As we have so far, we have a long temperature, precipitation and sunshine record. The temperature record goes back to 1813 on a daily basis. the precipitation record monthly from 1767 and daily from 1828. And the sunshine record from the invention of the Campbell-Stokes sunshine record is one of the first sites to get an instrument in February 1880, and daily records continue. And they are still continued with a manual observation. There was an observation done there at 9 o'clock GMT this morning. And part of that, and the broadening that I'm talking about, is that the pressure was maintained and measured as well. And up to now, we haven't done much with the pressure record. The pressure records going back to January 1811, 3 obs per day for pretty well most of the period up to 1924, so over 100 years of sub-daily observations. And of course, the metadata is really important, and that in itself is a presentation on its own for Oxford. So I won't go into it in too much detail, but a quick plug to the book, which has already been mentioned, but there's a lot of information available for Oxford metadata, and much of that is summarized in the book. One of the things that slightly surprised me about one of the reviews that the book had, commented that, well, this is all very well, but they haven't done much more than Manley and Gordon Smith did, which really surprised me, because Manley and Smith at the time were using monthly data. What we have done with the Oxford record is make it a daily data, and in many cases, like the pressure, it's now sub-daily data. So there is a vast amount more information, which of course has been available to us through using computers. So we come on to the Radcliffe scanning project, and this is something that Ed Hawkins and I have been working on for quite a while. And it started off with a NCAS grant of £10,000 at the back end of 2021. And we put the grant together for 2 objectives. One was obviously to try to preserve these priceless documents, some of which are getting on for 300 years old and are literally crumbling, and they wouldn't have lasted another generation. So we wanted to make sure that they were preserved. And then, of course, we wanted to create a digital archive to make it more available to people. It's not exactly convenient to have to go to the School of Geography in Oxford and try and get out a crumbling archive book to read something about the weather of March 1840 or wherever. So having done that, then, of course, we wanted to plan to digitize the content. So this turned into a commercial contract, which was tendered in October 2021, won by a scanning company in Glasgow called Orthodox, who did an absolutely excellent job, I have to say. If anybody else is thinking of things like this, I'm happy to put you in touch. And in all, we did 147 volumes, and Ed helped me load most of them onto the Orthodox van. We scanned a little over 32,000 files, 32,000 pages. So that included header and footer pages for some of the volumes. And we saved in the end 31,462 files. So scanned in high-res format, 600 DPI, so you can read all the fine detail on the page. So scanned in color. So where annotations were made in red, for instance, we can see the difference from the manuscript entry. So we scanned in high-res TIFF format, and we then downscaled slightly to JPEG and PDF, which are slightly smaller formats and a little bit easier to use. And I'm pleased to say it was all scanned within on time and within budget as well, unlike HS2, but there we go. So I've got a video, which I think, yes, is playing, which shows how it was actually done. So this is the page of observations from the Oxford Record Book for 1895, opening at the first page, 1st of January 1895. So the page is laid out on the platen of the scanner, and you can see there's a perspex plate put on top of it to hold the book flat so that it can be scanned flat. Obviously, taking care about not breaking the spine or anything. And then on the screen, the operator adjusts the pages so that we've got the page in the right place. And we scan both left and right pages. Sometimes there are manuscript amendments or additions on the left-hand page, which are relevant as well. And then, interestingly, puts in black sheets of paper around the page so that we get a good, clean, crisp image. And that also helps the contrast of the image as well. Now, this is a fairly time-consuming job, and I've got to say, I'm glad it wasn't me pushing that button 31,000 times. But at the end of it, we've got a series of very high-quality scanned records. So here's an example. One of them, this is one of the first sheets we scanned. This is Thomas Hornsby's record from January 1760. And you can see the 4 observations per day. You can see the barometric pressure, outside temperature, wind direction, an estimated wind speed. Needless to say, of course, this isn't Beaufort, because this is 35 years before Beaufort invented the wind scale. And a couple of words on the weather of the day. So this is getting on for 300 years ago. And I thought I would include the record from the observatory from 200 years ago today. So this is the 11th October in 1823. And you can see on the page, and I hope people online will be able to see it as well, the quality of the record, the quality of the handwriting is quite easy to make it out, with one exception. And this is this funny 8 on its side. If you can see it on the barometric pressure, you see the second digit is an 8. And it looks like an infinity symbol on its side. And Ed and I puzzled about this for a long time, but I have seen it used in other 18th century documents around that time, like on birth certificates and so on. So perhaps it was just a fad to enter the 8 on its side, but apart from that, it's perfectly legible. And of course, it's in inches of mercury, barometric pressure, and Fahrenheit for temperature. And at this point, I've got to say thanks to Richard Washington and Alex Black from the School of Geography at Oxford for their help and enthusiastic support in getting all this done. And there's the actual records digitized. So I'm going to talk about barometric pressure. So why focus on barometric pressure? Partly because we already have a good temperature, precipitation, sunshine record already digitized. But it's partly because we have records made with high quality instruments by professional observers and read very precisely. The barometer was read to 100th of an inch up to about 1838 and 1,000th of an inch after that. So these are very precise measurements. Now, Catherine talked about metadata, rightly so. We are unique in the Oxford record in actually having the original instruments still exist. And I don't think that's the case anywhere else. So John Bird's barometer from 1773 supplied to the observatory, the invoice for which still exists in the Museum of the History of Science in Oxford. The barometer still exists. I don't know whether it's still filled with mercury, unfortunately, but it still exists. Somebody could still read it if they put mercury back in it. And then there's the Newman Standard, serial number 1220, delivered to the observatory on the 28th May 1838, and it's still read every morning. And I don't think there's probably another meteorological instrument in the world that has been read every morning for that length of time. So in terms of the metadata, we still have the original instrument. Now I mentioned that we have records, sub-daily records, 3 per day, for most of the period from 1811 to 1924. And those observations are usually around 9 o'clock, 1 or 2 o'clock in the afternoon, and 9 or 10 in the evening. Now, the one complication with Oxford, probably with other astronomical observatories, is you need to be very careful to be sure what their time standard is, because every so often they revert to astronomical time, where the day starts at 12 noon. And suddenly you're wondering why all the maximum temperatures are occurring apparently in the middle of the night, because it counts from 12 noon instead of midnight. So once you're aware of that. Now, the main purpose of the current exercise is input to reanalysis products. So for those of you who don't know about reanalysis, talk a little bit about that. It's a combination of 2 words, retrospective analysis or reanalysis. And what it does is it combines the historical observations from observations such as the ones we've just been talking about with a modern weather forecasting model using data assimilation techniques. And there are several different versions of reanalysis around, but the one I'm going to talk about is what originally was called the 20th century reanalysis, which now goes back to 1806. So it's the 19th and 20th century reanalysis by now. And this produces really a synoptic chart, a weather chart, every 3 hours. So you can imagine the amount of supercomputer time that takes to do that for 200 years. And the main variables are surface pressure, sea surface temperature, and sea ice. And this is very good for looking at individual weather events across the globe. Now, of course, the resolution is much greater for the North Atlantic area. I wouldn't try and look at events in 1830 in New Zealand, for instance, because there's less data. There's a lot of ships data, but it's obviously very good for most of the North Atlantic. And one particular event I was going to have a look at was the Boxing Day avalanche of 1836. And for those of you who don't know it, this is the avalanche that has got the greatest death toll of any avalanche in the British Isles. 8 people died in the avalanche in Sussex, of all places, not the place that you tend to associate with avalanches, on Boxing Day 1836. Period of really cold, snowy weather built up a large cornice of snow on some of the cliffs behind Lewes. And on Boxing Day and the 27th, this cornice fell down on a village underneath and killed 8 people. So how good is the reanalysis at telling us what the synoptic chart looked like at the time? Well, here's the reanalysis output. Now, we shouldn't view reanalysis as just a clever way of producing an isobar chart, which is what I'm showing here, because of course it's a 3-dimensional analysis. So from this, I could have picked out temperatures, I could have picked out jet stream winds, whatever. But I thought it's probably best to show the surface analysis. And what we can see is high pressure over southern Scandinavia, strong easterly over the British Isles, northeasterly, depression probably over France, Switzerland area. And you can imagine, I'm pointing at the chart, but none of you can see that. You can imagine a strong, snowy northeasterly in the south of England. At this time of year, the North Sea would be relatively warm, so there'd be a lot of convective activity coming off in the cold airstream. And you can imagine a fairly large amount of snow in the south of England. Now, this looks very plausible, but we know it's not exact because we've got 2 other pressure records. We've probably got many more than 2, but we know of 2. The pressure at Oxford on this day, at this time, was 1005.8. And on the chart, Oxford looks as if it's going to be somewhere around 1016. So the gradient is actually tighter than is shown in the reanalysis. We also have the pressure at Exeter, which is about 1002. And again, that's about 10 millibars different from that. So if I was to criticize this chart, I would say that low is probably a little bit nearer the British Isles. The gradient is probably stronger, and that would account for why there was a greater amount of snow. But this is from getting on for 200 years ago. There's no way you could get a synoptic chart in any other way from that time without reanalysis. So it gives us a tremendous amount of data. So you may wonder how many pressure observations this is based on. Now, of course, it's not just those. There's a lot of ship's logs data in there as well, and that's probably what accounts for most of the detail that you can see. But in terms of the land stations in the British Isles, we have Armagh and Armagh only. That's all we have for 1836. And that's why the more stations we can get, the more pressure observations we can get, the more we can fill in the detail on some of these. Now, that's for 1836. And if we look at it on a worldwide basis, we still only have 6 stations, one of them in the UK. But by the time we get to 1881, partly due to the efforts of ACRE and various other digitization projects, those have increased very substantially. So by the time we get to the late 19th century, we've got a lot more points. Now, if we look in detail at the British Isles for 1881, just to keep you on your toes, the black points on the 1881 chart are the red ones on the left-hand chart, and the red ones on the 1881 are the ones that have been digitized since. So you can see we've more than doubled the coverage since that initial plot was run, and Ed and his team have been largely responsible for that. So we're gradually getting more and more pressure series before 1926. We've got quite a lot from 1926 onwards. But I've shown on this chart the Oxford record dashed to show how important it is in that particularly early period, up to about 1850, 1860, when there's very few other records. And bear in mind that this is a professional quality observatory, high quality instruments and so on. It should give an excellent record. Also on here, by the way, the orange plot is the record from Durham, which Tim Burt and I managed to recover from a Durham Observatory data set when we did the book on Durham, published last year, year before. And this was interesting because we had the digital record, but we didn't have anything to compare to quality control it against. And we used the reanalysis as a quality control mechanism. And your question earlier about, can you use reanalysis in another way to identify metadata? We found something very peculiar during the First World War, that the Durham analysis didn't appear to fit the reanalysis. And we weren't quite sure what this was. But at first, of course, you're inclined to think it was a change in observational process, or, lots of things happened during the First World War. There were less observers and so on. But eventually, to cut a very long story short, we discovered it was actually a fault in the reanalysis, and the Durham records were correct. And this was the first time this had actually been used to do that. So reanalysis can work both ways as a quality control mechanism as well. Now, clearly, once more and more of these are digitized, then the reanalysis will get better and better. And I haven't shown on here the excellent series that Richard Corns did for London, which goes back to 1697, 1692, sorry, 5 years out in 300 years. And that's, Richard's recently redone that by hours so that we have analysis that can be used to extend the reanalysis as well. So we're gradually getting more and more British records in there. So the task for this particular project, the Zooniverse project that Ed and I have dreamed up and put together, and Ed's done all of the work on doing the Zooniverse project, is to digitize the Oxford readings between 1828 and 1860, initially, those 3 daily observations. And the way it will work is that once you register and log in, you'll be presented with 10 days data, and you can pick the dates that you want, any date in the month. So pick your birthday or the wedding anniversary or whatever date, and it will then present you with a section of the logbook with that date in, and you just digitize those 3 records. And the little table comes up at the side, and you just type them in, and when you're done, press done, and it will come up with the whatever, the 28th of another month or the 28th of another month, and you just do that. It's quite addictive. I find every so often I'll do 10 minutes before tea or whatever, and then suddenly you find, gosh, that was half an hour later. But it is quite addictive. It's real data. It is quite addictive. So have a go if you can. So we've talked about the barometer readings. So why are we talking just about the barometer readings rather than about the 2 temperatures that you normally need? You normally need the temperature of the barometer itself to correct for the fact that obviously the mercury will expand, and you need the outside temperature to allow for the temperature of the air to reduce it to mean sea level. Now, I'll show the analysis that we did to think that we can do just the barometer readings, but if we do 3 barometer readings daily over that period, it's about 36,000 records. We do them 4 times through the Citizen Science Project to make sure that we have, if we did it just once, of course, we might get an error in it. So we do it 4 times. If all 4 agree, then we accept it as correct. If 3 out of 4 agree, we think it's probably correct. If only 2 out of 4 agree, then we look at it in detail. But if we do 3 daily barometer readings and 2 temperatures, clearly we've got 3 times as much data. We need 3 times as much digitization. So are the barometer readings alone accurate enough to be able to get us the reduction that we need? Well, the answer, of course, is no. But what we do have for the Oxford records are the means for each observation hour of the attached thermometer and the outside temperature. So what I did was I did an analysis of comparing what the actual mean sea level pressure would be using those 2 records, and then using the monthly mean of those two records and seeing what the differences were. And if the differences weren't too great, then we can just use the barometer readings. And that's what we found. We looked at 3 Januaries, a mild January, cold January, and an average January during the period we're talking about. And you can see that the differences are very small. In fact, 80% of the records are within half a millibar. And when you bear in mind that the average observer error on reading a barometer is about plus or minus 0.3 millibars anyway, it's very close. Now, also, when you data assimilate into a reanalysis, you don't take the exact value, you allow a bit of margin on either side, and that's about 1.6 millibars. And if you look at the plot, you can see it's actually about 0.3% are outside of 1.6 millibars. So these are fine. So that's for January, which would be the worst month you'd expect when the temperatures vary most. And then in January, we looked at, again, a hot July, cold July, and an average July. And it's pretty well the same picture. And again, 80% are within half a millibar. So do we think it makes that much difference? Frankly, it's close enough. It'll do, and it's a third of the amount of data to transcribe. So the next steps to this, phase 1 is the project that we've talked about, and I'll talk about that more in a moment. But we need to do the earlier records and some of the later records. Now, the format of the data changes, the way the layout of the sheet changes and so on. So it's not just a simple matter of just repeating the same thing. We need to allow for differences in the layout, but we will do those. Between 1861 and 1887, we have mostly 12 or 24 hourly observations. And we did wonder when we were looking at it, do we need more than 3 observations a day? Is that overkill? Do we really need 24 observations a day? But the answer is that not many other stations have nighttime observations. So it's very handy sometimes having observations during the night as well. So all in all, it's another goldmine of data. So we're looking for volunteers. You won't be allowed out of here until you sign up to do it. The site is weatherrescue.org. If you haven't already registered for one of the other citizen science projects, Ben Nevis, the Rainfall Rescue, the Daily Weather Reports, various other ships log, then sign up for there. There comes a little tutorial to explain what we need to do, and then just click through. It's very quick and easy. And in comparison with the size of the data for things like the Rainfall Rescue, which Ed will be talking about a little bit later, this is a minor project. It's a very small project, so we hope it won't take too long to do, but it will be a very useful source of data. So then, in summary, from Oxford, we've got a very good series of high-quality sub-daily pressure data from 1811 onwards. And thanks to an NCRAS grant to scan these, we managed to scan 32,000 pages of these, which have not only preserved these for forever, but now enables us to start doing work like this on them as well. So the phase 1 digitization project is now live. It went live a few days ago, and it will provide data for reanalysis projects. So as I say, we are looking for volunteers. And finally, just a few acknowledgements, of course, to Ed for doing all the hard work on the Zooniverse site and getting the NCAS grant in the first place, to Richard Washington, Alex Black from School of Geography at Oxford, and to Orthodox for doing such a great work. And there's a few references there for some of the other projects that we've done. And if you want to read a bit more about the Ben Nevis project or the British Rainfall project, then the references are up there. Other than that, Mr. Chairman, that's all I have to say. Thank you very much. Happy to take any questions. If you could try and make sure, if you ask a question, it's one I know how to answer, that would be even better. Thank you. Stunned into silence.
Hi, a very, very good presentation. I just wanted to ask, did you find any variations between individual observers? Because at that time, I think there were not any standard observing procedures in place. So did you find individual observers would do things differently, and that would affect the data itself?
That's a good question. And you say there weren't any standard observation procedures in place. That's true for meteorology, but for astronomy, there were very tightly defined ways of making observations. And these observations initially were made for astronomical purposes to determine refraction in assessing star positions. So they had a very tightly defined protocol of taking barometric pressure and outside temperature. So that was all they did for the meteorological part of the astronomical observations, but they did that with great precision. So there was some variation between observers, there always will be, and you can see that sometimes in the handwriting and so on. But we have to assume that those will cancel out. But it's a good question. There was another question, Mark.
So, Stephen, we discussed after Catherine's talk the importance of homogenization of data series. Are you planning to homogenize the pressure data here?
I think once we have it, Richard, then we will look at homogenization. I'm pretty sure that it will be surprisingly homogeneous. I mean, it's stayed in the same building all that time. There's been no moves of site and only the two changes of barometer. Yes, the observers have changed over time, but I'd be pretty surprised if it isn't very homogeneous. But we will assay it against the reanalysis and also against your London series and against RMR, and just see if anything pops out in terms of lack of homogenization. But yes, it's a good question, but fingers crossed it should be fine, I think. Question down here. Oh, come to you in a minute, I promise.
So it's interesting that you say that they use this data to measure refraction. Is it possible to work back from selected astronomical observations, assuming you knew where the star exactly should be, to work out how accurate the meteorology was, or to have some comment on it?
Well, I'm pretty confident about the instruments. I mean, we could measure to within 1/100th of an inch in the middle of the 17th century, and the middle of the 18th century, we could measure to 1,000th of an inch. So at the beginning of the 19th century, measurements to 1,000th of an inch, a well-known barometer type, like a 14 barometer, should be doable. I think trying to work it back from stellar positions, I suspect you'd need the intermediate calculation notebooks, which some astronomical observatories still have. Armagh Observatory have a lot of that kind of material. But I'm not expert enough to know whether you could work it back into an error chart for the barometer. But I suspect it's very small. It should be very small. Yes, finally get there, Mark.
It's a really boring question as well. No, it's just machine learning. Is that being used as a first guess or something to check this digitization? Because you'd think, you know, that Infinity 8 would be on every page kind of thing and that kind of thing, you know.
We did have a look at that, didn't we, Ed? For the Ben Nevis data, which was published data, so it was actually printed, and therefore, in theory, it should be even better. But we found that we actually got a better accuracy level using real human volunteers. But it was useful to have some kind of OCR to check for any gross errors. And things have moved on in the last 5 years with machine learning and AI. So I think there's a possibility there to look at it. But I don't think we could ever get ChatGPT to look at a page of the observer's books and actually translate them directly. The handwriting is beautiful, but it's not easy to read. Not yet. Maybe in another generation that might be the case, but not quite yet. All right, thank you.
Okay, let's move on. Whilst thinking that we look forward to the second volume of your Oxford book, Stephen, we knew there was more analysis going on. Okay. I think it's right this afternoon that we take a global view and look at the status of global temperature series, particularly in view of events around the world this year. So with pleasure, I introduce Dr. Michael Taylor, who is a Senior Research Associate at the Climatic Research Unit at the University of East Anglia. And he's involved with the GLOSAT project, the Global Surface Air Temperature Series. And he's going to be looking at the contribution of machine learning to filling gaps in an extended global temperature series. Michael.
Thanks. Hello, everyone. So just start by saying thank you to many colleagues and collaborators, so Tim Osborne, Emily Wallace, Phil Jones, David Lister and Ian Harris at UEA, and Kevin Cowtan at University of York, who basically wrote the code we use to do the machine learning, Colin Morris at the Met Office, Ed Hawkins and the rest of the GLOSAT team for supporting and the guidance, and to Trevor Davis at the Tyndall Centre and John Pomeroy in the University of Saskatchewan in Canada, and an artist, because I'm going to show you some artist paintings, a climate mural called Gennady Ivanov in Norwich. So to advance, do I press the right arrow on the screen or this? Okay, thanks. On the remote. Okay, I did two. Thanks. So yeah, so I'm working on updating the global station database of monthly mean land air surface temperatures at the Climatic Research Unit crew at UEA for the GLOSAT project. This is the web page for GLOSAT. And the dataset contains 11,865 stations. The earliest record is the Central England temperature record, which starts in February 1659 until yesterday, because it's now updated daily since 1722, which is fantastic. And I would just like to highlight a couple of our more extreme stations, but the long ones, I'll explain what I mean in a second. So for example, the hottest monthly average that we have is actually in Saudi Arabia at a station called Alula, but it was a 1/10 of a degree higher than Death Valley. But the Alula station only had 9 years of measurements, but the Death Valley we have over 100 years of data, which is a longer record. So what I've done here in this box is to highlight our longer extreme monthly station records. So the red splodge on the world map is the hottest record at Death Valley. The blue dot in Antarctica on the right-hand side is at Vostok, and that month had an average in August 1987 of -75.3 degrees. It's incredibly cold. And Vostok is also famous for having a almost 3-kilometer long ice core drilled there, which allows us to understand a lot about our climate past back 800,000 years. So Vostok's a very important station. They all are. Our highest station is at Bange in Tibet or China. It's owned by China, and that's like green spot up there. And it's at 4,700 meters. We actually have a really short record in Chile called Malalal, which is at 6,400 meters. But again, it's a very short record with just a couple of years. I should mention that. Well, our most remote station is Easter Island, which is called Mataveri Isla de Paz. It's from the Chilean National Meteorological Service. It's a long way. It's about 3,600 kilometers from Santiago in Chile. It's a long way. Our northernmost long series is at Svalbard Lufthaven, and but we actually have more northern records than that. Svalbard's at 78 degrees north, but we have a record at Alert, a station in a Canadian station called Alert, which is 36 years of data. That's 83 degrees north. And we have a really short record. We have a station at the tip of Greenland called Cap Morris Jessup, which is at 84 degrees north. And then we have a really short record from Macedonian National Meteorological Service, which is a drifting station, and that's at 86 degrees north, so it's really far north. But we only have 2 years of data, unfortunately, for that record. Our most southern station is the South Pole, at the Amundsen Scott. Thank you. So our records have been assimilated over many decades by my colleagues, and they come from many sources. So there's an ecology of sources of data that is acquired as part of CRU-10 and our global station database. Some of the stations are keyed in manually. I've done some myself, not many, but a couple of tens of stations. The most recent one I keyed in was for Kendall from the John Dalton diaries. We also have data which comes in every decade from the world weather records, which is WWR. That's a very important source of data for us. And we also, another thing that we spend quite a bit of effort on is fixing metadata. So, for example, we have stations where which have a lat and a long and an elevation, and the record, of course, and a station code, which can come from the World Meteorological Organization. And when we look at the physical location from the lat long, it doesn't match the metadata entry for the name of the station, or sometimes not even the station code when we cross-check it with the WMO record. So there are disparities in the global station database associated with metadata, and careful attention to the metadata is very important for understanding what's going on where around the planet. And I had an immense difficulty in a very high Arctic region called Franz Josef Land, where we have now got over 11 stations. But some of them were owned by Norway, some of them were owned by Russia, and there was a bit of a mangling of station codes, which meant stations were mislocated, and it took a bit of effort to figure out what went where. That's done now. So we spent quite a bit of time on metadata fixes. Which brings me to the general philosophy, I would say, that is adopted at CRU, which is we quality control all available sources of data and try and merge them in with National Meteorological Services, with that provided by National Meteorological Services. And in terms of data rescue, we're trying to recover historical data, so new sources of data. We're trying to repair data that we have, which is erroneous, which could be on a metadata level, or it could be to do with inhomogeneities. I'll talk about that in a moment. And then we have another concept, which is the release of data. So we have data that we have constrained in one way or another. So one way you could constrain the data is by putting a first year, which is reliable in a time series. And that would be an example of a constrained station record. And if you can correct the early data in that record, then you could release that constraint, and that data would then be assimilated into, it would be an update to the record. So there are many different ways that there's an ecology of sources that feed into CRU-10. And at CRU, we also are adjusting for exposure bias. I'll mention that in a moment. And also to do homogenization with something called local expectation kriging, which I'll also talk about in a moment. In terms of potential big gains in the future, I would point to digitization, because citizen science and AI parsing could potentially give us, you can't see it because the box is over the numbers, between 100 or thousands of new stations, potentially more. It's really important for engagement with people and the educational aspect for people to learn about climate science and weather. And it also provides new capacity in terms of the capability capability of models, so it can improve the capacity of our modeling. Very important. Another potential big source is cross-project mergers. For example, there are many projects that have large databases of stations. For example, the historical CLIM or HCLIM is a very big one. We're independent, so we have independent sources, which is important for cross-checking and calibration. It's good that we have that independence, but cross-project mergers could potentially release hundreds or thousands of stations as well. Yeah, and every now and then the National Meteorological Service, if based on personal contacts, can suddenly release hundreds of stations to us, which is great. Yeah, so in GLOSAT, we're back extending crew temp from 1850 back to 1781, which is the GLOSAT period from 1781 to the present. We, for each station, assign a first reliable year for the time series. There are 11,865 stations. That's quite a task in and of itself. In many cases, it's just equal to the first year of the data of the time series. We also assign a homogenization level to each station. Another thing we do is combine stations to produce a composite series, which are in climate sensitive regions. So for example, at Blue Hill Observatory, on the cover slide, we have the observatory on the top of Milton Hill. We have created a composite because Blue Hill Observatory is important because it is the longest continuous record of observations in the United States, dating back daily to 1st of February 1886. And we have managed to extend it back 100 years to 1786 because we had unlocked we had unlocked a pile of sub-daily data from some amateur observers in the United States, because at that time, from 1786 until 1829, there were observations in New England on the east coast of America were done by medics. So there were people who had other jobs, but they went out 4 times a day in one case and took measurements for almost 3 decades, which is an incredible level of commitment by someone who's not who wouldn't consider themselves their primary job as being a meteorologist. I think I just find that absolutely incredible level of dedication, and that provides us with data which is consistent because it's typically done by a single or, in a couple of cases, a couple of observers. It's very helpful for understanding inhomogeneities in the time series. And in the case of Blue Hill, it is the data from those practitioners that provided the anchor point that we needed to be able to lock down the rest of the time series at the right level to, yeah. So that's a great, for me, it's a great example of the importance of amateur meteorologists who are very diligent and expert in their practice. Yeah, before I move on, sorry, I should also mention that at Crew, we have a PhD student called Emily Wallace, who's submitting very soon, the end of November. And Emily did a fantastic job of studying the metadata of nearly 5,000 stations and looking at when the thermometer enclosures changed type. So she studied the evolution of the transition of thermometers from one enclosure type to a Stevenson screen throughout the history of each station for nearly 5,000 stations, focusing mostly on extratropics. And this is her plot here. It's not my plot, it's Emily's plot. And you can see that most of this, by around 1918, most of the stations had Stevenson screens. And why is this important for us? It's because not only historically understanding the history of these changes is important. But the fact that there is a transition from one enclosure type to another introduces a bias or an inhomogeneity in the time series, and that bias is sizable. We found it to be of the order of, on average, across all the time series, to be of the order of 0.3 degrees centigrade. So it's quite a sizable source of bias. And Emily did this amazing job of modeling the seasonal characterizing and modeling the seasonal nature of that bias so that we could adjust the time series for exposures, which we did. And what I've been doing is looking at how to rescue the anomaly time series. So it's one thing having a series of observations that measure absolute temperature, and it's another thing converting them into temperature anomalies relative to a reference period, like 1961 to 1990, which is the WMO standard reference period. There is a challenge, because if your station does not have observations in that period between 1961 and 1990, then you do not have the reference values you need to set the level for the anomalies, because essentially you subtract the 1961 to 1990 average from the temperature measurements to get the anomalies. Yeah. So what we found is that 3,430 stations all fell into that category. We just couldn't calculate anomalies for them because they did not have observations within the 1961 to 1990 window. Which is all those white dots. All those dots there are the efforts of meteorologists taking measurements, and we had time series of many, many decades that we just couldn't use to calculate the global mean surface temperature. We couldn't average, you can't average the station temperatures unless you convert them to anomalies. So there were lots of stations that we were not able to use. So we had to find a solution to that. And with a colleague at the University of York called Professor Kevin Kautan, we've been applying ordinary kriging. Because we're in the Geological Society, Krieger was a modeler who developed a method for that helped him in the 50s understand where would be a good place to mine or drill a bore to find gold nuggets, for example, knowing other sources that you'd already mined. So essentially it says that given spatial information around you, can you use that to get an estimate for another location? That's what kriging does. That's what the kriging model does. So we use that principle to take advantage of the fact that for any station where we don't have the 1961 to 1990 values, we do have neighbors. There are neighboring stations. So we take advantage of the fact that some of the neighboring stations do have measurements in that period and are close enough to the station that we are holding out or trying to set the level for. So if you do that, then you can fill the gaps. And so kriging provides an estimate every single month from 1781 till the present. And in doing so, it provides us the ability to fill in these gaps. So the top plot shows the stations where we had data that could be converted into anomalies, which is the orange dots. The white dots are the stations that we didn't have, we couldn't convert to anomalies, so we couldn't rescue those. And at the bottom, after using kriging, then we could rescue the majority of the white dots, which is great. We're using most of the global archive now in the calculation of the global mean. So in terms of so having done that, the next question is, well, if you've now got a new series of anomalies, how homogeneous is it? So we took a look at every station and assigned a homogeneity code. The top two are homogenization codes 0 and 1 mean that homogeneity was not assessed at the source. So it's either we just don't know, or it wasn't assessed, but we do know it came from a reliable source. Well, that would be the orange one. And then the other three categories, 2, 3, and 4, the blue and the light green and the dark green, are stations where they've been the homogeneity has been assessed, and inhomogeneities have been corrected. And there's if they've been corrected at the source, but we don't know the method used, that's the pale blue stations. So there were some large-scale regional efforts by the Nordic countries and China and Russia. So those big cluster of blue dots in the top map is that category. So they've been homogenized, but we don't know how. And then the green, the light green, a lot of those in America. There's a couple of them in South America, for example, and in Sweden, Norway. They've been homogenized and corrected, and we know how. We know which method. Did they use pairwise homogenization algorithms or something else? It's been documented, and we know that. And then the last category is the dark green. So you can see them in Southern Europe in the top plot, and some in South America, and some in the southern parts of Africa. These are stations that we homogenized ourselves, the whole of Australia, one by one. But if you convert those codes into a binary display of stations that have and have not been homogenized, you end up with the bottom map. So we can see that most of the stations in red, these are not homogenized, tally with the new acquisitions. Those dark blue dots, if I flick between them, you can see that most of our new acquisitions are unhomogenized. So in the temporal domain, so I'll run through the rest of this quickly because we're coming up to a break, and there's still some other stuff I want to show you on art, if I have time. So in the temporal domain, we can see that the white curve here and here is stations going from 1781 to the present, every decade. How many stations we don't have pharmacological references for? In other words, how many stations are we not including in the calculation of the global mean temperature? It looks like it's going up in a curve like this, but when you look at it as a proportion of how many stations are available, it actually reveals a double peak. So there's a cluster of stations in time, clustered in time, between, can't see, around 1820 and 1870 there. And then there's a cluster here between 1975. These ones are just short series. So these are time series from stations that started around 1975 until the present, or from automatic weather stations. And they just don't have enough overlap with 1961 to 1990 to allow us to calculate anomalies. If they start in 1975, at most they can only have 15, which is it's our threshold. We need to have more than 15 values to calculate a WMO reference value. These are just early records that don't have enough neighbors. When we apply LEC, then we can start to solve this problem, and we are able to save more and more stations, both the early ones and the more recent ones. These are really hard to save because quite often they're in very remote locations, like on the gigantic continent of Antarctica. So we talked a little bit about that before. So looking at it spatio-temporally, I just pulled out 4 snapshots of the land record. There's no marine data here. So the first one is at the time of the eruption of Mount Tambora in April 1815. We can see that most of the stations are clustered around Europe. There's a couple on the east coast of America. And then if we, it's very hard to, using only land-based meteorological weather stations, it's very hard to get a good understanding of what the response of the atmosphere is, and also the oceans, is to a large planet scale eruption like the Tambora, just from the land data. The wonderful thing about GLOSAT is that we now have lots and lots of data from the sea, from ship tracks. Now, didn't want to show anything here because we have other colleagues who are going to show about the progress on the ships, the GLOSAT data. So we do have a lot more data than this to look at things like the response to Tambora, but this is what the land temperature record gives you. And if you wind the clock forward to 1873, because this year was 150 years of the inauguration of the Quarterly Journal of the Royal Meteorological Society, if I'm not wrong. So this is, we can see that the global station network has spread across the mid-USA, with more stations appearing in Eurasia, a couple appearing in South America, one in South Africa. Lots associated with new marine passageways. I'm looking for another word. I did write it down. Yeah. So basically, the arrival of new ship pathways led to settlements and the establishment of new stations in Australia, New Zealand, and other important parts of the planet. In 1938, at the time of Guy Callender's amazing estimate of the global mean surface temperature, he used 147 stations. The stations are really well distributed all over the planet. And at the time of the 2018-03, March 2018 was when we had the beast from the east. From the land record alone, so without any reference to sea data, we can already discern, just from the land data, the negative North Atlantic oscillation, and the influx of the cold massa there into our sector, just from land stations, which is great. So the reason why Guy Callender's calculation is so important is because even though he used only, you can't see it here very well, but it's 147 stations in 1931. That's the red curve. It overlays quite well with the GLOSAT record at that time, taking stations up to 1935. That was GLOSAT version 4. And in 1961, when he revisited this problem, he used 400 land stations, which are these. We think, we're not totally sure, we think is the match with GLOSAT is almost perfect. So you might ask the question, well, how many stations do you need to get a good estimate of the global mean surface temperature? Why do we need so many stations when 400 can do the job for you? Well, we have to bear in mind a couple of things. One is that his calculation was limited to plus and minus 60 degrees. So from up to 60 degrees north, so up to the edge of the Arctic Circle and down to the edge of the Antarctic Circle. And if you want to have a good representation of the global mean temperature in data sparse regions like in Antarctica, then yeah, you need a lot more stations. However, he did this by hand. I don't know if he used an arithmometer or a IBM 608 to do his calculations, but his result is astoundingly good, and it just shows how precise he was in his work at that time. I just really love this, and yeah, it shows us how robust the global mean surface temperature trend is to the number of stations, provided that they are well distributed spatially around the planet. Yeah, so this is where we're up to. The Crew 10 data land record is the purple line. Is this one here? It goes back to 1856, not 1850, because at that time we made a decision not to include southern hemisphere stations that we didn't have climatological reference data for. And our work extending in GLOSAT, extending the crew time record back in time to 1781 is this blue curve. So you can see these oscillations, which are partly related to spatial sparsity, but more related to this period being a volcanic, having a lot of volcanic forcing. There were some very important volcanoes in this period. And the red, so that was the red curve, and the blue curve is what we get when we add in these stations that we have rescued with the calculation of the 1961 to 1990 averages. Thank you. I'm aware I'm going over time, aren't I? Yeah, it's also my ability to speak, but yeah. Can I show one or two very quick slides? Okay. So in terms of applications, what we've also done is use observations to constrain future temperature projections. So if you take a model, I took a model, climate model called FAIR, version 1.6.4, and ran it 1,000 times to generate 1,000 ensemble members. And then if you constrain those ensemble members to the past observations, then you eliminate a lot of ensemble runs which are non-feasible, and that allows you to have a improved estimate of future warming for different scenarios. And if you, that's what we have here for SSP 370, 7 degrees of forcing. 7 watts per square meter of forcing, sorry. This is the head crew T data, and you can extend the data back in time by adding data sets. So if you add the multi-proxy record from pages 2K, the pages 2K consortium, it takes you back to 0, common era. And then you can supplement that with ice core data to get back to 800,000 years before common era. And you can go right back to the beginning of the Kenozoic, the age, people call it age of mammals. If you then include oxygen isotopes from benthic forams and deep sea marine organisms, the shells of deep sea marine organisms. So why did I do this? Partly because I like extending stuff forwards and backwards in time, and to put the temperature record in context. But also because the Norwich City Council asked us to make a mural for their debating chamber. So that's what we did. So we then converted these into an analog of Ed's warming stripes. But we used the anomaly from the Paris Agreement period, which was 1850 to 1900. So white here is the average temperature in the period 1850 to 1900. Anything bluer is colder, anything red is hotter. And this is going from 65.5 million years ago out to 2200. And the top plot is showing the SSP 370 projection. And then a local artist called Gennady Ivanov painted it. Yeah, so he made the skyline the colors of these stripes. This is 10 meters long, it's really big. And then he has the Norfolk coastline here with all sorts of historical events, like this is a tree where cats met under this tree in 1573. Yeah, the Norwich was founded in the year 500 here. There's a Frankenstein somewhere here from Mary Shelley associated with Mount Tambora. There's lots of stuff in it. I'm really sorry. And then we put it on the wall. So now it's permanently inside the Norwich City Hall. And you can go and visit it. We welcome you to come and see it. Yeah, there's the website. So I don't know if this is being recorded and people will be able to have access to that. Thank you. And yeah, I made an app so that people can go and look at the raw data. So you can zoom in on this and look at different things like the interglacials, and the future warming relative to the past. We're going to zoom past all these multiglacials, potentially, if we're not careful. Yeah, hitting past climate analogs, which are going to cause us a lot of problems. Yeah, we have two futures, and I urge everyone to talk to everyone they love and everyone they know in their communities that we need concerted action to reduce emissions, so that we can stabilize the climate in the future, rather than have more runaway climate situations. Thanks very much. There are things, I will wrap up with this slide if I may. So, so data rescue is really important, and what we need is new data rescue in regions where we don't have stations. We would ideally like an acceleration of decolonization, so that pre-independence data, Catherine mentioned this a little bit in her really nice talk. So pre-independence data from countries, and post-independence data from countries can be merged together to improve the representation of temperatures around the planet. Thanks very much for listening to me, and welcome any questions or comments. Thanks. Let's begin.
With great pleasure, I introduce Professor Ed Hawkins, Professor of Climate Science at the University of Reading. Ed's well known as the originator of the climate stripes, of course, but he was also a lead author for the IPCC sixth assessment report. He leads the Weather Rescue Project at Reading as a whole, and today he'll be talking about the highly successful Rainfall Rescue Project run through the pandemic. I remember I did try to register for this as a volunteer, and I received the message, everything's finished. It was so successful. We've had our 16,000 volunteers, and it was over in 16 days. So I'll hand over now to Ed to give us more information. Thank you.
Thank you, Julian. So yes, I'm here to talk about rainfall rescue, and a little bit of motivation is this picture from Reading from March 1947. And the reason I like this picture is because it contains my house. I don't think my house actually flooded during this event, but you can see very extensive flooding across Reading at this time. And of course, we are very interested in flooding and also drought. And of course, rainfall is the key aspect we need to understand if we are to think about what the likelihood of changes in floods and droughts are. So our national infrastructure do think about these types of aspects to our what happens to our water. So flood planners are making decisions based on estimates of what a 1 in 200 year flood will be, and water companies are legally obliged to think about resilience to a 1 in 500 year drought. Now, both of those I think are quite hard to calculate, especially when our records are not 500 years long. And so we do have to think about longer context as much as we can if we are to inform these types of decisions. And we do have quite a long time of measuring rain in the UK. This is the first measurement of rain in the UK. Richard Townley started recording rainfall at his hall in Burnley in 1677. And he published the observations in the Philosophical Transactions in 1694. And here you see the monthly rainfall amounts in thousandths of an inch recorded by Richard Townley for this 10-year period. So we do have some very, very old rainfall observations. This is just one location that may not be particularly useful for understanding trends or anything like that, but it shows how long we've been trying to think about how much rain has fallen on these islands. And the current state of play, or the state of play that existed before the Rainfall Rescue Project, was that we had the Met Office produced the England and Wales average monthly rainfall, and we have that back to 1766, and that's a big spatial average every month across England and Wales. So that goes back a very long way, but it's not very detailed spatially. It's just one time series. We also had the monthly gridded rainfall data series back to 1862. And there are two examples of the maps from that data set here. One is, or two very wet months. One on the right is February 2020, and one on the left is October 1903. And October 1903 is the wettest UK month on record still. And on these maps, you can see black dots representing where the observations are that go into producing the very, very detailed maps. And you can see there are more dots in February 2020 than there are in October 1903. We have better coverage in this example in February 2020 than we did earlier on. There's also a daily version of these maps going all the way back to 1891. You can download that. So this is the type of information that we had available to us at the time, a couple of years ago. And if you look at the time series now on the monthly data availability, these are the number of rain gauges that had monthly observations available before we started rainfall rescue. And so we had 19 stations available at the start of the UK series in 1862, going up to several thousand in the 1970s and 1980s, and then drops off more recently as we've lost the manual rain gauge network slightly. So the 3.4 million monthly observations that go into producing those very detailed monthly maps. But it also looks like we started recording rainfall in 1961. Of course, that's not actually the case. We didn't suddenly send out thousands of rain gauges in 1961 and ask people to start recording the rain. The data is missing. It's lost. It's not available to scientists. And of course, that data was not completely lost. It was carefully curated by Catherine and her team in the National Meteorological Archive. And these are what we call the 10-year rainfall sheets. And Catherine and her team have 66,000 sheets in the archives that were originally collated by Simons and the British Rainfall Organization starting in the 1860s. And so these sheets, carefully stored, were scanned in 2019, and therefore they became available to us to be able to use again. And there are about 2,000 sheets containing data before 1860. So that would allow us to extend backwards in time those very detailed maps of monthly variations in rainfall. And there are around about 5 million observations on these sheets had never been digitized, apart from probably a few examples. But essentially, none of the data was available to science. And here is one example of a page. This is Reading Forbury Gardens. This is the closest rain gauge to my house. And this data would have been new, right? So this is the 1890s, the data recording in Reading every month. We have lots of useful information. We have the latitude, the longitude, the observer's name, and all the other details about the rain gauge and where it was situated. This is a great example of very valuable data which we did not have available to us before we started. There are older sheets as well. So from Reading, where I live, on the left, we have an example from Reading Athenaeum, going back to the 1830s. They took observations in the centre of Reading for an extended period of time. And on the right-hand side, we have even earlier observations taken by a certain Luke Howard, who many of you will know the name, back to about 1800. And so we have lots of valuable information that is not available to us, or was not available to us. And so the question is, how do we transcribe 5 million handwritten rainfall observations accurately, efficiently, and cheaply? So AI at the time, and still, I don't think cannot yet do this. We have to rely on manual keying, transcribing by people who can read the handwriting. And so we asked for help. So it was very lucky timing in many ways. So Catherine and her team had scanned the sheets in late 2019, and we learned about that scanning in early 2020, just actually as the pandemic was beginning. We suddenly realized that this was actually going to be an amazing opportunity as we got locked down and were stuck at home. Many people needed a distraction from what was going on, the horrific news around the world, and many people had spare time on their hands as well. And so we very quickly put together an effort to try and ask for volunteers to help us transcribe these observations. And we luckily enough got some help from the BBC, Jonathan Amos was delighted to write about something that wasn't COVID. And so that was fantastic. So he actually put out an advert on the BBC to ask for volunteers. And of course, we love talking about the rain in the UK. And so we got thousands of volunteers. It's fair to say that we did not expect the speed and the reaction that we did get. I thought this was going to take months and months and months. This was an order of magnitude bigger than anything we'd attempted in the past. And I was not expecting what happened next. So in all, we had 16,000 volunteers take part. Between them, they typed about 100 million keystrokes in just 16 days. And we completed the transcription of all 66,000 pages. It turned out there were 5.28 million monthly observations on those sheets, and 4 different people typed every single number so that we could be sure about the data. And of course, there were occasional typos, but we could pick those up because 4 different people did every one. And we got better than 99.5% agreement. It's about 0.5% we did have to look at manually again. But essentially, virtually all of the observations were transcribed by the volunteers very accurately for us. But that, that I thought that was going to take months, and it didn't. It took 2 weeks. But then came actually the difficult bit, which I hadn't really planned for because it had gone so quickly. But of course, what you realise is that for a particular location, such as this is Reading Waterworks on Bath Road, again quite close to my house. Of course, that site took observations covering 6 different decades. And so if you wanted to build a time series of the rainfall of that particular location, you had to find the 6 individual sheets, piece together the transcriptions of those sheets that have been provided by the volunteers to produce a time series. And here is the time series then that was put together for that waterworks. It used 2 different rain gauges, and so there's 2 different colours. But here we have a 60-odd, 50-odd year record from that one site. And you'll notice, of course, the other piece of information we need is the latitude and the longitude. There's no point knowing a name of a station. We need to know where it was, both in space and, of course, in time. And so in many cases, the latitudes and longitudes were not written on the sheets. It's invaluable metadata we need. And in some cases, the latitude and longitudes were there, written down. Some of them were accurate, some of them were not, we believe. But many cases, we had no spatial information. And so what it needed actually was other volunteers to help us find, locate, and quality control the data. So we have ended up with lots of time series of rainfall, and once this process has been completed. So here is that station in Reading Forbury Gardens. We saw the 1890s page earlier. It has pages covering lots of different decades back to the 1860s with some gaps. But there we are. We now have a new time series for Reading. And even further back at that other sheet, Reading Athenaeum, we have some data from the 1830s and 1840s, again with some gaps. But this is the data that we have available, which can be pieced together with all of the other series to produce a much longer coherent series. And here's Luke Howard's observations from Tottenham, covering about 3 decades, right at the start of the 19th century. And so once we've put together all of these series, we can then examine what's happened now to our time series of available data. So the orange line is what we had before we started Rainfall Rescue, 3.4 million monthly observations. And the black line is what Rainfall Rescue recovered. So, and that we've now quality controlled. So there's 4.9 million quality controlled monthly observations spatially located, which we've added to the database and handed over to Mark and his team to use with the rest of the data that's available. And before, we had 19 stations available in 1862 at the start of the UK series. We now have 767. And the earlier data means that we can push back those very detailed maps of monthly rainfall all the way back to 1836, where we have 149 stations covering the whole of the UK and Northern Ireland. At this point, we do have to give very special thanks to 8 very particular volunteers. So Mike, John, Jill, Jackie, Richard, John, Ian and Tim, and Richard is here. Thank you very much, Richard. And I suspect there's others online. So thank you very much to those of you who are online at home. So these are the 8 volunteers who stayed with the project for 2 years and did a lot of that work to locate in space and do the dedicated research on the observers' names often, and search through ancestry information, through maps, through census information to identify exactly where all of the stations were. And so we've been able to recover the space location for the vast majority of those transcribed observations. And that's taken an extraordinary amount of work by those 8 volunteers. So this project would not have been possible without them. And we owe them a great deal of thanks. And I'm very pleased that the Royal Meteorological Society gave them a special award this year to recognise their efforts, and they are co-authors on the paper as well. So that's a very important point that we have to note. So where do we have the data now? So here are 2 maps showing where the rainfall gauges are located. First of all, on the right, we have 1862. So this was the start of the UK series, where we only had 19 stations before. These are the 760 something stations that we now have, and they do cover essentially the whole of these islands. There's maybe gaps over the Highlands perhaps, but they pretty much cover the country, including all the way to the Shetlands and Outer Hebrides and everywhere. At the start of the UK series, now in 1836, we have pretty good coverage. There are some gaps, notably South Wales, Kent, Northeast England, and perhaps again a bit in the Highlands. But there are data in the Outer Hebrides and the Shetlands, for example. So we are covering north to south extremely well. And the reason we can't go back any further is because in 1835, we don't have any data from Northern Ireland. Both the 2 Northern Ireland stations drop out. And so this is as far back as we can go if we want the whole of the UK. So this allows us now to bring in that longer term context for changes in rainfall across the UK. So this is the change in annual rainfall in the UK all the way back to 1836. We see a long-term trend to wettening in the UK. It's increased by about 14% since 1836 overall. We see the wettest year ever is still 1872. We knew that before. But the driest year on record is now 1855, and we did not know that before. And so that is a new driest year on record, even though it occurred a long time in the past. So that's the annual picture. But where in the year does that change occur? It actually mainly occurs in the non-summer seasons. So here's the winter time series, and we see that winter rainfalls increased by about 25% over that time. A very strong trend in winter rainfall, and we also see increases in rainfall in autumn and spring. But in summer, we basically see no significant trend if we average over the whole of the UK. There are trends in certain regions towards drying, in some regions and slight wettening in others, but summer rainfall, we don't see any significant trend across the whole of the UK as a whole. But I think more importantly, what this data allows us to do is to look at extremes. We're always interested in changes in extremes because they are the things that cause us the biggest problems. So as I've mentioned these 2 years already, this is the spatial map of rainfall for the driest year on record on the left and the wettest year on record on the right. Pretty close together in time, actually. But 1872 had twice as much rain as 1855. And so here we are now, have a map of where the rain fell those 2 particular years. And so if you're interested in extremes, these are the most extreme years that we can find. If you're interested in extreme months, we can do the same. We can look at August 1947, when there was hardly any rain across the country, compared to the wettest month on record, October 1903, where we had 220 millimeters on average across the country. And it's worth noting that we've only had 5 months with more than 200 millimeters. 3 of those have happened in the last 15 years. We are getting wetter. We're getting more months that are extreme, but the wettest on record is still 120 years ago today. Isn't that nice? There we go. We can also look at individual months that we did not have access to before. And so two example months. We had two very, very wet months back to back at the end of 1852. And several of the UK regional records for months are in this 2-month period. So in the southwest and then or some parts of the northwest as well. These are the wettest months on record, and they occurred next to each other in the end of 1852. And so if you are planning for floods or so on, then these example months where we had very, very wet conditions are really of interest if you want to ensure that your flood defences are appropriately high, for example. And so we did not have access to these maps before. So this is new information to help provide useful information to understand our risks. And at the other end of the scale, we also have new information about droughts. And so if we look at the consecutive 3-year periods, and the driest 3-year period on record is 1854 to 1856. And the second driest is 1887 to 1889, both of which obviously a very long time ago. So if you're a water company interested in drought, this is, I think, really useful information to know that we could get a 15 to 20% rainfall deficit sustained for 3 years. And those examples are a long way back in the past, and we only now have that data available to us. Of course, the climate has got wetter since these periods, and so we may not expect to see such dry conditions if those same weather patterns happen today. But I think the 1850s drought is as intense as anything else, even accounting for the fact that it was drier conditions on average at the time. So that's really valuable to have. So I think we've probably now done the job with monthly rainfall. There may be a couple of series here or there that we could add, but I think essentially we've completed tick off monthly rainfall off the data rescue list for the UK. What we haven't yet done is we can't do that same tick for daily rainfall. So if you visit Catherine in the archives, she can show you shelves and shelves and shelves and shelves of sheets of daily rainfall observation from many of the same sites. There are 300,000 pieces of paper in the archives containing, we think, around about 100 million daily rainfall observations, starting in around 1850 up to 1960, to fill in that spatial gap and temporal gap that we have in our observations. These sheets have not even been scanned yet. It would cost about £100,000 to scan. So if anyone's got any spare change, it's an expensive task to even scan these 300,000 sheets. And I think recovering this data would be, immensely valuable for the UK to understand changes in daily rainfall extremes, which are so important for climate risks today. I think the transcription of those sheets is too big a task for volunteers. I think the Rainfall Rescue Project was immensely successful, but that was 5 million. This is 100 million observations. Okay, many of them are zeros, but I think we need some help from AI to read these 300,000 sheets once we get them scanned. So this is, I think, our next major challenge in the UK. Scan these sheets and then find some AI help with some volunteers probably to do the difficult bits, to rescue that data and send it to Mark and his team to improve the daily rainfall grids as well. So just to summarize, I think it was an amazing project to be part of, to see so many people volunteer, step forward to help. The volunteers have made an invaluable contribution to our science. They have enabled us to extend our detailed reconstructions of rainfall much further back in time. And this picture in the background is summer of 2022. And I was listening to the radio, and this is July, I think. The newsreader on the radio said, the Met Office had just announced that this July was the driest July on record. And then she said, and these records go back all the way to 1836. And that would not have been possible before. And that, there was a quiet moment of quiet satisfaction. No one else would have noticed who was listening. Right? But anyway, so Rainfall Rescue has extended those records back, and we can go earlier for some regions. and it enables us to put recent events into a much longer term context, and will in the future certainly help us understand risks from floods and droughts. We still have an enormous job to do in the archives, to scan large parts of those archives to enable the material to be available. And then we definitely need some AI help to recover what are billions of observations that are in the archives untranscribed. And you know, in the UK, we have some of the longest, best detailed observations anywhere in the world, and we need to make use of them as much as we can. So I'm just going to highlight actually some couple of things from the chat, because during the project, the volunteers were transcribing data, but also chatting with each other as well. And there was lots of amusing anecdotes in the sheets which they spotted. This one is about Belmont Abbey, where the abbot had reported that they couldn't measure rainfall because there was a bullet hole in the rain gauge. And this led to a whole thread of very interesting observations about weird things in the records. And many of those made it through to the final paper describing those interesting observations. But they also noted things like this, that they were transcribing 1925 and they noticed that June, hardly any rainfall anywhere. And so they were learning about rainfall variability while they were doing the transcription. And there's lots of other these notes in the chat about someone found when their father had inspected the rain gauge, which is rather remarkable. And then one person at the bottom who essentially they didn't feel of any use anymore because they'd retired. But by doing this project, they felt useful again. And I think that's a really important part of why we want to keep volunteers involved, because they can make amazing contributions, but they get benefit, enormous benefit from helping us with our science as well. Thank you.
All right, thank you very much indeed, Ed. And we have a question on.
Yeah, question from Kevin. Just regarding the Citizen Science Project, were there many images of sheets that were of such poor quality that you could not include them in the whole process?
No. Yeah, I mean, they all have the same format, which is extremely helpful. They all had, months and years in the same places. And so we're able to show the volunteers the whole of every single page and just ask them to type the values for 1 year. Yes, there were numbers that were hard to read in certain places, and there were disagreements amongst the volunteers who had typed those particular numbers in a small number of cases. But what was helpful is at the bottom there was a mean or a sum of the rainfall for the year. And so if there was disagreement about a particular number, often the sum was able to resolve the differences that the volunteers had seen, and we could work out virtually all of the months from that.
So this is from Tim. 5 million observations with a 99.5% agreement between the 4 transcribers means 25,000 observations with some disagreement. What did you do about those?
So that was thanks to our 8 dedicated volunteers who pieced together the sheets. So once we were able to find, say, the 6 sheets for a particular site, the data was concatenated together, and then in the spreadsheets that were produced, any disagreement was flagged. And so wherever there was a flag, the volunteer who was working on that particular site would revisit that page, look at the image, look at the other data, check the values, check the sum at the bottom, to see if they could work out what the value was from having the complete context. If they couldn't work it out, we deleted it, and there's a gap. If they could work it out, then we resolved those differences, those 25,000 differences. Yeah.
Just of interest, did the sheets that were scanned match up with all the data that's in the British rainfall books?
Yes. So essentially they come from the same source. So these sheets were published in British rainfall, but British rainfall only often had the annual values in many cases. So yeah, so we actually used British rainfall a bit to check some of the numbers in a few cases where we could do that. But yes, there were more sheets than are published in British rainfall. Yeah, so British rainfall is only a subset.
Just one last, okay, let's.
Yeah. And thank you, Ed. Whilst acknowledging the value of the monthly rainfall work that you've done, these are calendar months.
Yes.
And I know from experience that that can sometimes hide very wet spells that happen to fall in both months. So will your daily data project allow you to do sub-monthly periods, 10 days, weeks, or whatever?
Yeah, absolutely.
Thank
So, I mean, that would be the value of having the daily data. You know, we could look at 1 day or 5 day or weekly or 10 day or whatever period we would like to look at things across month boundaries. Yeah, absolutely. I don't know how to do it yet, but yeah, it would be amazing to get done.
Okay, in fairness to the last two speakers, we have to move on fairly quickly now, but I would like to say, I think we do notice 1836, Ed, as the extension to the rainfall records, and we are very grateful. So I think we'd all agree, impressive stats, and I did intend doing a plug for the Geoscience Data Journal at the beginning in my introduction. If you haven't seen the displays outside, then there are still a few articles present, including the article that Ed co-authored last year describing the rainfall radar rainfall rescue project with Catherine Ross and many others, and Stephen Burt. And if you look at it online, that is a very, very interesting read to continue what Stephen's just said. Okay, our next speaker then is Dr. Praveen Taleti, lead researcher on the Weather Rescue at Sea project at the University of Reading, perhaps in some ways a successor to the Rainfall Rescue project. So today, Praveen will talk about that project, which is accelerating the recovery and use of ships' logs. So I shall hand right over now. Thank you.
Hello, everyone. I'm Praveen. I'm a postdoctoral research associate at University of Reading. Along with Ed, we've been working on recovering historical observations as a part of GLOSAT project. So before actually going into the project itself, I just wanted to touch on what makes the ship logbook so interesting. So for that, I would like to take the example of two ships called HMS Erebus and Terror. So these were built like a battleships. So they were found suitable to go into polar exploration. So HMS Erebus and Terror first went to Antarctic under the Captain James Ross Antarctic expedition. So they attempted 3 times to penetrate further south than anybody before them. And even though it failed to locate the magnetic South Pole, but it did a lot of other things. It found the ice shelf, which is now called Ross Sea ice shelf, and also found a lot of new plants and animals. So in a whole, it was a success. And it really opened new things to the science, where when people thought that Antarctic as a continent doesn't exist. So it disproved all those things. So it's probably quite a good depiction of the conditions that the ships found themselves in the Antarctic. So just imagine that they were just sail and steam ships, and they had to struggle with all these rough seas and ice conditions, but they still did a good job and came back safely. So as soon as they returned, they went to the other end of the world, as if they were not just satisfied with Antarctic. So within 2 years of returning, they went again to the Arctic, to this time under the captaincy of Sir John Franklin, and this time to explore the Northwest Passage, which probably many of you would know that it resulted in tragedy for all of the people on board. So they came very close to finding the passage, but the weather, the ice conditions so bad that from the beginning they had all these problems. And in around 1848, they were abandoned basically, and the crew members all either died of cold or hunger or starvation. And yeah, and it was a bad end for those people. But the ships were literally frozen in time, because they were stuck within the ice, and as we researchers have found that they were abandoned, and they just sunk bottom of these small inlets in the Canadian Arctic. And they were discovered quite recently. So HMS Erebus was discovered in 2014 and Terror in 2016. So as you can see in the small picture that I've placed here, you can still see the plates, which were a tradition in those times to have a plate with the names of the ships and the captain and things like that, specifically made for that ship. So there's so much things that we can look at now and understand, and it brings together a lot of historical and social aspects, information about that times, about the ship and their lives on board. So the ships themselves tell us such an interesting story. So just imagine what the logbooks would tell us. So I'm showing you the logbook page from HMS Terror on Ross Antarctic expedition. So you would have usual information about date, weather observations, the remarks that for example, any particular interesting plant they saw, or animal they saw, or for example, they found this big ice barrier, they would write that on the remarks. And I would like to take your attention here, which says 76 degrees 45 minutes south, so which was the farthest south at that time. So we have the documentary evidence to say that this is what they have achieved. So they would be able to say this is the contribution we are making. So these logbooks are not tell us interesting stories, but also record very useful weather observations as well. So there are probably hundreds of thousands or maybe millions of logbooks like these exist, and nobody have seen them literally since they were written, because they were, once they come to shore, they were deposited in a big archive or a library, and that's end of that. And there are so many observations that can help us understand past weather, but they are still in paper forms, as previous speakers have spoken about different aspects of how they can help us understand the weather and the climate of the past. But we need to come over the first obstacle of actually getting those observations back into a form where researchers and scientists can help them. So as I said, like there are millions of logbooks, so not one person can do it, or even a group of people can do it. We really need a sort of a big community sort of effort to do it. So we need to, first of all, want to do collectively. We want to scale that process so that we have not just one, for example, not just 16,000 logbook, 16,000 images like in rainfall rescue. There are probably hundreds and thousands, and we want to do it efficiently. We want to get those observations into the system as soon as possible, as efficiently as possible. So we have a answer all these things, to give us all these facilities, we have Zooniverse platform, so which essentially does that. So this is a project called All Weather World War II. So this is how the Zooniverse page looks like. So you have a sort of a home page of the project, and it tells you about if you click on these links, it tells you about what the project is about. You can classify, you can go onto the form and fill in the observations that you see, and you can chat to researchers or other fellow volunteers, or you can do different other things as well. So what is All Weather World War II? So in 2017, National Archives in the US released about 200,000 documents, including ship logbooks. So because they were related to World War II, they were classified for well over 70 years. So only in 2017, they were released, and NOAA funded a project called All Weather World War II to extract these observations from these logbooks. So our colleague from NOAA, Dr. Kevin Wood, initiated this project and set up this project to gather observations from these logbooks. So what kind of observations these logbooks have? So they have barometer air pressure, barometer from air temperatures, wet and dry bulb temperatures, SSTs. And also they have metadata as well, what the ship type was, what instruments they were using, and what methods they were using to observe these observations, and why we want to use that, because a lot of reconstruction have shown that there is an anomalous warmth during the World War II period, and that we think because the techniques were changed so rapidly during the World War II that we haven't managed to make right corrections, so that we have some observations which are taken by different instruments or different methods, but we haven't corrected that so that it is in line with overall observations in the long term. And also we are interested in something called El Nino, which is a climatic event that happens in the Pacific Ocean. And we know that there was a severe drought in Australia around World War II. And there were droughts in the Europe as well. And there are a lot of extreme events that happened in around the El Nino climate event. But we know these from other sources, but we don't know exactly how long the El Nino event was, or how strong it was, because the observations that tell us from this region were totally absent from the observations, the current SST data sets that we have. So that's our motivation to do it. So what is the logbook format? So if you look here, you have dates, different columns for different weather parameters, and the location. So I would like to take your attention here, which says 7th of January, 1941, which is exactly the day the Pearl Harbor was bombed, and these ships were in Pearl Harbor. So just imagine that you are in the harbor and it's a normal Sunday, and you're just thinking about normal things, and suddenly you're bombed and all the ships around you are on fire, and all you're thinking about is taking next weather observations. So the level of dedication and sense of duty they had towards the work is truly tremendous. I mean, they were still taking observations, but later on they moved away from the port because they thought there might be more bombing. So they were in port in the morning, and when bombing stopped, they just moved out. And this this logbook on the right-hand side shows something called war diary. So towards the middle of the war, they thought that the positions should not be on the logbooks. It should be in a separate document, because they were fearful that if enemy did capture a ship, they would know the movements of the fleet. So they separated other observations from the position, which sort of like increased our work, but that's fine. We can deal with that. So this is how the Zooniverse page looks like. So we would ask a question here in the form, and corresponding logbook would be shown here, and the volunteers would write in what they see on this page, and they would just click on done, and we would have their observations. So what ship types and what were the ships and where were these instruments placed? Because a lot of these, as I was saying, corrections depend on what instruments they used and how high they were placed from the sea level. So because we know what ships they were, we can make estimate what ship types they were and their maximum speed. And because speed, the estimation of speed helps us to estimate the heat loss from the SST's measurement, so that we can adjust for that heat loss, and also how high they were from the waterline. So with all this metadata, so we can make the right corrections. So as an example, this is a Stevenson screen on the side of the bridge island. So even though the instructions were that it should be painted white, but sometimes because they were in a war, they didn't want a white little box sticking onto the side of the ship. They just painted it black or something to mix with the camouflage. So yeah, we can't blame them. And yeah, and also they were asked not to put these Stevenson screens next to the galleys, because they would catch the artificial heat from inside of the ship. But I mean, it was more convenient probably just to come out from here and take the observations and go in again. So yeah, so you have to deal with all these things that nobody tells you, because we can only know these because we have the photographs, but they are not anywhere mentioned on the logbook. So we have to keep all these things in mind while making the adjustments. So there were about 30,000 images, logbook images that we used over the 5-year period from 1941 to 45. And this is the sample ship track from 2 ships that I wanted to show you. So this is USS Pennsylvania and USS Tennessee. So the colors denote the year. So starting from 1941 to 45. So as you can see, they actually cover the whole Pacific Ocean, and Tennessee even did the circumnavigation at the end of the war. So they started from west coast of America, going to Far East, Indian Ocean, southern tip of Africa, back to east coast of America. So we have a good coverage, spatial coverage of the from the global oceans. So if we combine everything together, so these are the total observations binned into 2-degree latitude longitude box. So we can see there are the most observations in around Hawaii and the Pacific Ocean, in the Far East, in the Philippines, and around South China Sea. So this is the area where we have very few observations for the World War II. So this data set will really help us understand the weather and the climate of that time. And to just give you a summary, yeah, there were more than 3.7 million unique weather observations that came from this project. And these observations will go into ICODES, which is a big international observational data set, and that will help us to understand the past climate. So the next project I wanted to talk to you about is weather rescue at sea. So this is kind of very similar, but we wanted to look at the observations in the 19th century, because that's where all these observational data sets have a very sparse coverage around the globe. So we wanted to target a specific time period where there are a fewer number of observations, like 1960s and 70s, which are relatively poor compared to 1853 standardization, and focusing on air temperature or SSTs, which give us a lot of information. So they were based in, these logbooks come from UK Hydrographic Office, and we selected these logbooks for their simplicity of their format. So there are 2 day per leaf, 4 days per page view, and up to 6 4-hourly observations, and more than 15,000 images were used for this project. There are probably thousands more, even, I mean, maybe 3 times more. So this is how they look like. So you have columns for each weather parameter, and these are the R's. So you would have position here, dates here, name of the ship here, and where they were based, and remarks at the bottom. So dates, temperature, and winds as well. So we are still, sorry, I forgot to mention that this project is now finished. And because of wonderful volunteers from Zooniverse, we were able to finish this in a year time, year and a half. So it is finished now, and we are in the process of processing that data that we have. And as Ed was saying in the previous talk, that we need to process for different errors in the transcription process. There might be duplications or wrong numbers input. So how do we come to the correct number is by matching different transcriptions with each other and building a consensus, so that we select the one which has majority of the numbers. So for example, this is a ship called Landrail. It was in the Atlantic, in the Caribbean. There's Revenge in the Mediterranean. This is the Far East. It goes to UK, from Japan to UK, and this is again Atlantic. So till now we have processed about 55,000 observations, and they, as you can see, they pretty much covered the whole ocean. So once we finish this processing, I think we would have around 3 million observations covering all ocean basins, Atlantic, Indian, and Pacific, and they would help us fill in the gaps and estimate the long-term changes in the climate. So what are the lessons to be learned? So if you are interested in, or if you're thinking of starting a data rescue project, crowdsource extraction data rescue project of your own, so we can give you some pointers. So design of the workflows should reflect the structure of the logbook page. So workflows is basically a compartmentalized task that you ask the volunteers to do, so that, for example, if you want to ask about temperatures, there would be a temperature workflow. You would ask about temperature, they would go and do and give you temperature extraction. And also it helps to give a context to the logbook pages and the the purpose of the project, and it actually motivates people because logbooks on their own, without any background story attached to them, it makes no sense to anybody. So it's really helpful to carefully think about the project, tell them as much as possible about the project, what you expect to do in this project, and where this data will go. So it really motivates people to spend their time and effort to do the extraction. So yeah, and also grouping similar transcription tasks together helps people to focus on what they want to do. We have seen that some people just likes to do temperature. Some people just like to do air pressure. It's just the way it is. I mean, some people just like that. So we don't know why, but yeah, it helps them choose what they want to do. And they should be broken down into smaller chunks. You don't want to ask them a full page of data in one form. You just lose track of the point that you were in the page. So people would just leave without finishing the task. And lastly, I think we should be able to store ideally all images that were used in the project in a publicly accessible location, because the way the Zooniverse works is it shows you random logbook image. And if you want to go a day earlier or a day after, it's not very easy you can go if you know how to search it, but it's not very easy. So if we can put all these images in somewhere where people can just slide through chronologically through the logbook images, then it would give them some sense of overall picture what's happening. For example, if you see a storm and they're wondering, oh, what happened? I see a storm. Was there a storm tomorrow as well? So they might want to see the next day, even though Zooniverse is not showing them the next day immediately. So yeah, all these things help. So I'm happy to give suggestions or advice or on any on running the Zooniverse projects if anybody is interested. Yeah, and thank you for your attention.
Okay, time for 1 or 2 questions. Just follow.
Yes, thanks so much. That's an interesting talk. I just want to ask you, what's the relationship between your 2 projects and the Acre project? And it's the data from well, you've got 2 projects, Acre project's another bigger project. Are the 3 project data sets being combined in some way, or are there plans to do that?
I think we are not formally part of Acre project, but this work, the last one I showed you, was part of a GLOSAT project, which Ed and I are working together. So I think Acre is also trying to. So I think my understanding is Acre sort of brings people together, try to form collaborations. So once the project gets initiated and gets completed, the data it's supposed to go into a big database. And in this case, we are trying to push this because these are marine observations. We are trying to put them into ICORIS data set. Or maybe Ed would like to add here.
Yeah, that's the answer I was hoping for. But it's difficult to get data for ICORIS at the moment because technical challenges and people moving. It's very difficult at the moment. And I haven't attested to anything. Okay, working. Okay, thank you. Something online.
Great. So it starts with a comment. This is from Naveen, just saying wonderful work. You know, these projects, obviously, you know, obviously you get the input from the individuals, but they learn as well. It's an education for them. But I guess the question really then to yourself and Ed is, when you're structuring these projects, how do you ensure both the accuracy of the transcription, but also that it's a rewarding educational experience for the participants? Do you think about that as you're going into it?
I think there is a chat forum within the project, and we do try to answer and sort of like educate people on different aspects of the logbooks, or even the history of the logbooks. So I think it's the logbooks in themselves have so much information, and people educate themselves by reading the remarks or trying to understand the weather was like. So yeah, we do try to cover that aspect as well.
Thinking of the time, if you forgive me, I think we ought to really move on as to Mark, but thank you very much indeed.
Thank you so much.
Okay, right. Well, our final speaker is Dr. Mark McCarthy, Climate Science Manager at the Met Office, leading both the climate monitoring area through the National Climate Information Centre and also climate attribution now at the Met Office. So he's going to be talking about the benefits of data rescue to the national observation system and climate monitoring, why it is so valuable. Mark.
Thank you, and thank you to the organisation of this meeting and an invitation to speak today. As Julian has said, I was sort of invited to talk from a user's perspective. In this context, climate science and climate monitoring as a user of data recovery and data rescue activities and their value for our science. And I'm going to talk quite a bit about activities within our national climate monitoring and acknowledge my colleagues in the National Climate Information Centre, Mike, Dan and Stephen, but not exclusively, so also touch on a couple of the wider contexts. So at the Met Office, Hadley Centre within our climate programme, but broadly speaking, climate research more generally, our core aims are around monitoring changes to global and national climate, determining the cause of these changes and developing the numerical climate models and processes to project future change, to inform policy and to inform risk assessments under a changing climate. And as the National Meteorological Centre and also with a climate research, producers of weather services, but also climate services, it's bringing those things together increasingly, particularly how we communicate that to the wider community and the wider public. Most recently, as an example, we have experienced the joint warmest September on record for the UK, equaling a record set not that long ago in 2006. So through our monitoring activities, we can see how this September fits into the context of over 100 years worth of historical data for the UK overall, but we can also, using the combination of the observational data and climate models, try to understand the context of that and estimate that actually in a natural-only climate or a pre-industrial climate, the chances of experiencing a mean temperature as high as we have this year is exceptionally unlikely. Whereas actually nowadays in our current climate, there's maybe around a 3% chance of experiencing a September as warm as this year. And that is likely to, and that will become more likely in the future as our climate continues to change. So within climate monitoring, as well as the national work, we maintain and continue to improve a range of both UK and global data sets that looking across a variety of metrics, but also a variety of platforms. So as well as a lot of the in situ observations we've heard about today across land and oceans, also working with platforms, the satellite data, upper air observations, upper tropospheric humidity, for example. So a lot of this work is on how best to bring together these different measurements from different parts of the observing system, from different eras of time, to provide those consistent and complete records and picture of our climate through time and across the world and across the country. And to build a better representation of the uncertainties inherent in those data sets and those climate monitoring. And I should also acknowledge, I guess, within that context, that data rescue and data recovery, a lot of what's been discussed today has been looking very much back into pushing the boundaries of the historical records. But we should also acknowledge that there's been huge efforts for more modern platforms, or what we might consider more modern platforms. So data recovery activities for the early satellite record, for example, really valuable for climate science today. And acknowledging that the work we do now in securing the observations we currently take for future generations is equally important. So the output of this work and for monitoring the current state of the climate, sort of encapsulated to some extent by our state of climate reports. So this is really to how we can inform policy development, provide that policy relevant science, but also provide contextual information, whether that's at a local level or within national climate planning. So within the climate monitoring team, we produce the state of the UK climate, but also contribute to the global reports coordinated by the American Meteorological Society through their BAMS publication and the WMO State of Global Climate to really provide that pulse of climate change. More colloquially, within the National Climate Information Centre, so our remit is for national level climate monitoring. Catherine earlier already alluded to our national memory. So we have a role within the digital memory and providing an authoritative source of UK climatological data products, increasingly important in an age where misinformation is becoming more rife, that we can provide those authoritative, traceable, reproducible statements and data sets for monitoring climate that can allow people to put weather and climate events into their climatological context and also enable society to better understand and respond to the risks and opportunities that climate variability and climate change are posing for us. So one of those key outputs, as I mentioned already, we provide an annual publication. And my colleague Mike Kendon has been the lead author in this series, where we put the most recent year and most recent decade of observations into that longer term historical context. And these are some examples from the State of UK Climate 2022. So the UK's warmest year on record. But also including the unprecedented heat wave from last year, so 40 degrees recorded for the first time, other extreme events such as Eunice. But increasingly, we are experiencing events that are pushing ourselves outside of the envelope of historical climate. So having these robust historical records encapsulating as long a period as we possibly can is really important. And the image in the bottom right here is also then attaching that to the fact that within climate science, we're also providing that future context. So putting past, present, and future into that context of how we respond to a changing climate. And again, so here for 2022, the first year where the UK mean temperature exceeded 10 degrees. So within a natural only climate, we put an estimate on that about being something like over a 500-year return period. Whereas in our current climate, actually our current estimate is that may be something like a 3 or 4 year return period now. whereas in actual fact it's only happened once so far, but we expect to happen much more frequently going forward. In the context of UK climate monitoring, as has already been mentioned today, we have records going back much further. So we do have multi-century records. So we are benefiting from the data recovery activities of people like Gordon Manley in the sort of mid-20th century, doing extensive and painstaking recovery of data from archives across the country to put together the Central England temperature record. So we can also put, you can see right at the very end of this series, 2022 as the record warmest year in that series, in over 360 years of temperature observations covering the UK. And so in terms of the timeline of instrumental observations, particularly at a national level, we are looking at the sort of 17th century to present day as our sort of instrumental monitoring period. So a few kind of timeline activities noted here. A few of these have been mentioned today already, but the development of instruments that we sort of are recognizable by today's standards, barometer, thermometer, anemometers, we really put that sort of the mid 17th century. Fahrenheit and Celsius then followed in the 18th century. And the earliest sort of recognition of the value of having networks of observations can also be pinned to those early scientists like Robert Hooke and others as to the value of taking these measurements. But it wasn't until the establishment of meteorological offices, both in the UK and elsewhere, that we came into the era of systematic networks of observations for climate monitoring, and then the sort of work of people like George Simmons and others in collating information and recognizing the value that these historical series have. But this sort of recognition that we're looking back over 360 years. So it's also the observations that we're taking now and the work that we're doing now in terms of documenting our climate is going to be of value for 300-400 years into the future. So we also have a role for providing the requirements of what will the requirements for scientists, climate scientists in 2300, 2400 for understanding the climate of the 21st century be, and are we ensuring that we are retaining that memory of our weather and climate appropriately. So I've already mentioned the Central England Temperature Series has a key beneficiary, flagship climate data product that has benefited from data recovery activities over many decades, starting from Gordon Manley's groundbreaking work in the 20th century. But here just a schematic representing the contributions of different station records to the daily Central England Temperature Series. So this is building on work undertaken by one of my first bosses, actually, David Parker at the Met Office, who developed the daily temperature series back in the 1990s onwards, and the recovery of various diary and archival documents to produce these series. So while the modern series is based on stations at Rothamsted, Stonyhurst and Pershore, we can see that actually there is still value to revisit and supplement further data from these earlier eras, which would still be valuable for providing a better grounding of the uncertainty and our representation of some of this earliest period, the 17th, 18th century in particular. Another key product that Ed has already discussed today that we produce for monitoring our climate is our HAD UK grid dataset. So a key motivation for this dataset is to recognizing that the distribution of observing stations over land has changed over time, where they're located, how many there are. but we have a requirement to provide some robust national and regional scale statistics on our climate monitoring. So the HAD-UK grid is an effort to take our irregularly distributed set of land surface observations through time and space and interpolate those onto a regular grid. So we do that to a 1 kilometre grid across the UK through the data set that we have. And the purpose is this then, meaning that we can produce and pull out statistics for something like UK rainfall that is not overly sensitive to the exact distribution of stations at different points in time. So here's just a few snapshots, again, taken from September 2023 and for periods 50, 100, 150 years ago, showing how the sort of distribution of stations has changed for those different periods of time. From a peak in the 1970s of nearly 5,500 stations, providing very dense coverage and less so elsewhere. Ed has already presented essentially this figure, so I can't understate the value that the Rainfall Rescue Project and the work that Ed, the team and the volunteers contributed to that has made to our national record of monthly rainfall for the UK. So this is another representation showing the sort of the before in the dashed yellow line for monthly rainfall, and then the two sort of versions of data from the first tranche of the Rainfall Rescue Project, and more recently in our latest version published this year of the data, which has taken us up to in excess of 5,000 rain gauges for much of the 20th century. So a really transformative initiative for monitoring our rainfall data over the year. The blue curve on this chart is the daily rainfall series. So re-emphasizing the case put by Ed earlier, that actually that is the next challenge, because this cliff edge for daily rainfall is not a reflection of how many observations are actually available. It's just a reflection of how many is digitally available for modern climate research. So we still have a lot of work to do there. So picking up another example of the benefit that this work has for our climate monitoring, there's nothing particularly special about September 1873 other than being 150 years ago, but it's a nice example to sort of pull out the impact that these data have. So what I'm showing here on the left is the sort of before distribution, so before we incorporated the rainfall rescue data, the set of stations we had numbering about 200 across the UK, and the representation of rainfall anomalies for that month. And on the right is showing the distributions of stations. Now we've incorporated the rainfall rescue data set, and their color contours, again, showing the anomalies. The two panels on the right are the same, but with the stations removed, just to see the differences. So what this is sort of demonstrating is that the broad scale picture is consistent between the two. We're getting this representation of relatively dry month across much of the Midlands, central and northern England, and these wet regions across parts of the far southeast, and also across eastern Scotland, which was notably wet and more than twice normal rainfall in some areas. But the Rainfall Rescue Project is kind of adding the detail to the spatial representation of that. So while the national scale figure was not much changed by the incorporation of all these additional data, users with looking in particular areas may have noticed sort of larger differences between the two as the rainfall rescue is providing that increase. And we can look at some sort of statistics across the data set. So through a process of a leave one out process where we sort of individually exclude each individual record and then can estimate
an overall root mean square error across the network for the different versions of the data set, we can demonstrate that the Rainfall Rescue Project has significantly reduced the uncertainty in our historical rainfall data. So the grey curve on this chart is the version of HadUK grid data set before the Rainfall Rescue Project, showing the sort of root mean square, overall root mean square error for the interpolation, and the blue and orange curve are after the incorporation of those data. So for our 1873, 150 years ago, the 1870s, the error in the current version is sort of more similar to the early 20th century in the previous version. So we're improving our representation of the data. The data recovery has also improved our representation of extremes. So in the early talks earlier today, talked about breaking new records and the frequency that we're breaking new records. We're also breaking new records by historically by introducing the new ones. So again, without repeating Ed's presentation, for our annual rainfall series, now 1836 to 2023, the wettest and driest years are 1872 and 1855 respectively. And this is important contextually for how we understand risks of future change. So the grey shading are representations, a plume plot of the future projections. This is not the full range of that. So it's also a reminder that the extremes can still sit outside the mean change that we can expect in a future climate. Daily rainfall, as I say, again, an area for considerable future development. So we do have a daily rainfall series from 1891. This is an example from an extreme event, the flooding in Norfolk and Norwich in August 1912. And the animation here is a comparison of the map of that event in the British Rainfall article sort of at the time, the contemporary representation, and the current representation in our HadUK grid product, rescaled to sort of reflect the same contouring. And we can see, again, this consistency even across from an event over 100 years ago, of our ability to capture and represent quantitatively how extreme that event was. And we also do that for modern day extremes. So for the UK overall, our wettest day was on the 3rd of October 2020. And that was reported at the time that the rainfall across the UK that day was enough to fill Loch Ness. And using the observational data and the climate attribution system, we can look at how climate change has sort of influenced those extremes and how extreme they are in the context of an extensive climate data record. But we do still have further work to do to improve our representation of early daily rainfall extremes, particularly because they can be more spatially localized than the monthly extremes. So other extensions of UK monitoring through data recovery activities. The monthly weather report collection has provided further monthly temperature data. So our temperature data set for the UK extends back to 1884. So another record within this series is now 1892 as the coldest year. The sunshine data most recently has been extended back to 1910. So previously the data were to 1929. So now, although not, we're including the two extremes of a very exceptionally sunny but not record-breaking 1911, and the very, in contrast, the subsequent year 1912 exceptionally dull. I'll also echo the value of metadata, as has been raised by Catherine, Ed, and others today. And again, some nice examples that were reported in the Hawkins et al. Paper for the types of challenges, the real world challenges of making observations in the past, but actually some of these still happen to rain gauges today. And it's a sort of reminder of the richness of this metadata and acknowledging we really do value it and the work that the volunteers did in not only pulling out the data, but actually pulling out some of these records. And this is a photo from, I think, thanks to Catherine for this photo of the Seathwaite site. So this is all really valuable information for us, but we still have the challenge of knowing how to systematically interpret and use all this rich metadata when we're developing these national and global scale climate monitoring products. These charts have also already been presented, and so I won't repeat that, but yeah, consistent with the findings of others and with from Mike's talk earlier in the global context, this sort of potential warm bias in the 19th century observations, and there is where we can take that further is both through the exploration of the metadata and understanding the instrumentation, the exposures of the UK sites at the time. But actually, we also, in this particular study, we focused on the long-running stations, so stations that had at least 50 to 100 years worth or more of observations. So it's a relatively limited sample of data back here. So there's also more work to be done to increase the availability of daily observations going back into the 19th century, so that our methods, whether they're statistical or through the metadata for understanding the homogeneity of these series is particularly valuable to us. So I'm just going to kind of finish up with summarizing what those ongoing scientific challenges are really for data recovery activities and our use of it. So yeah, can't reiterate enough that further recovery for national records of daily and sub-daily observations is going to be really essential for the assessment of extreme events. The recovery of the station history information is really valuable, but also working out how we can most effectively use that information and the richness of it and the variability in it, the range of information that is there to exploit. How then this feeds into our understanding of the homogeneity and the uncertainty in these data sets, their quality control and evaluation, and continually always working on how we can improve the accessibility for the wider community to access and make use of this information, and really be able to trace it back from a kind of a statement about a record month to linking that up to archival material from the 19th century that when, say, an event of that magnitude might have last been seen. And to conclude, our climate is changing, and data rescue and recovery has really provided an essential part of the evidence basis, not only for past climate change variability and extremes, but also feeding into how we interpret that in the context of present risk and future potential change. So our recent climate has been warmer, wetter and sunnier than in the past. And temperature extremes are particularly changing much faster than averages, particularly in this part of the world. And we're seeing increased likelihood of extremes in both temperature and rainfall. So it is the bedrock of climate science. It has been this data recovery activity, and we do still have a lot to learn from our historical archives in that context. Thank you very much.
We do have to vacate by 6 o'clock. There's another meet as soon as. Okay, right. Maybe time for maybe one question to Mark then. Mark.
Thank you. Very nice talk. Okay, so there were trends that we've seen, but with this new data, now we've got the extreme wettest and driest years being in the 1800s. Does that have impacts for attribution results and research, and also impacts for how you portray sort of climate change to the public?
Well, kind of yes on both counts, in that it's important context that we're capturing those extremes. In terms of I suppose that the consequence for attribution and the representation is also acknowledging the range and variability within our climate, what that means. So a lot of the attribution sciences are the likelihood of events occurring, but that doesn't preclude the fact that such extremes may have happened in the past. And it also provides opportunities if we can bring together these observations, but also reanalyses and incorporating that to explore, well, actually, if 1855 happened now, what would it look like? As much as, say, what would now have looked like if it had occurred in the past. We can kind of work across, so that try to explore some of those what ifs. What if this event happened again in our changed climate? And I think they'll be quite powerful. They're quite powerful ways of using these events, tangible events, to communicate how climate change has changed perhaps both the likelihood of that occurring, but also the magnitude or the potential impacts from such an event.
Okay, right. Well, as there were no immediate questions, I think I'm getting the hint that the next group want to set up. Can I take the opportunity then finally to thank all of our speakers this afternoon, to thank Hayley and Catherine from the Society, to thank Liz for staffing the laptop, and at least wrapping up now, at least Mark, you can get home to the West Country once again, hopefully, if the trains are recovering. So thank you very much for all your questions as well as the presentations, and I think we ought to probably close there then. Okay.